entire event. So, and then the questions, you can either put them in the chat or you raise your hand and then we call you up and then you can ask questions. Yeah, let's just directly jump in. So we have, for the opening now, we have 3 short welcome messages. And I see that Gabriel is also here. I saw Leo, and the first one will be, I'm sorry, I have to let you present yourself. Just go ahead and jump into your presentation. So have a good time, everybody, and talk to you in between the sessions.
Okay, thank you, Kirsten. I'm not sure about how to pronounce your name, but we've met a couple of times and still I have problems with that. But anyway, so languages are not very easy. And I think that my name is Szabolcs Cifrus. First, my introduction. I'm the director of the Institute of Nuclear Techniques of Budapest University of Technology and Economics, which is a very nice institute, a very nice university in the center of Budapest. Unfortunately, you could not come to Budapest for this occasion due to this COVID situation, which is now a little bit better, of course, but we were afraid to organize this thing on site. And I have to tell you that for me, it's a fantastic thing to see that so many young people are interested in nuclear topics. And I think that this occasion is a great opportunity for you to learn, and not only to learn things and study new things, but also to meet each other. Of course, now not in reality, but using Zoom. But I think this is better than nothing, and still we have to make use of the possibility that we have now. Originally, I thought I would talk now a little bit about the training reactor and our university, but tomorrow, actually, I will have about 20-25 minutes to talk about our training and education, and also about the training reactor and our projects. And I think that it would now be a repetition tomorrow, so I think I will take this starting speech very, very short. And what I would like to tell you is that I think that I need to thank. So this is a big and a huge thank to Cilla Pesniak, who organized for you. So that was one of the, I would say, the main organizer of this event. And I have to say that she has done a fantastic job putting together the program for you and organizing all the lectures and exercises that you will have the opportunity to participate in. So I think that the program is amazing. I think that within a week there is. I think that it is this program ensures that you will have the opportunity to learn a lot of things, and I'm sure that you will have a good time, not only to learn but also sometimes to learn new things and things which will be useful for you in your later life and later career during your university education or later in the let's call it real life. And I think this is all I wanted to summarize now for the moment. And again, a big thank you all for you organizing, Cilla, Kirsten, and everyone who is participating in the organization of this event. And I would like to say thank you, ENEN, and for the support, and also for the EU for supporting this action. And I wish you a very nice week, spending your time fruitfully learning as much as possible. And I wish you success in this week. Have a nice time. Thank you.
Thank you. So, okay, I will hand over to Gabriel. Gabriel, I think I saw that you're here.
Yes, Kirsten, I'm here. Thank you very much. So good afternoon and welcome everybody to this second meeting, which is, I didn't want to say second very important meeting, but indeed it is a very important meeting. It is organized in the framework of the ENEN Plus project, a project which deals with attracting nuclear talents or attracting people to the nuclear field, or developing nuclear talents and supporting, especially supporting nuclear talents, supporting people that wish to have a career in nuclear. A while ago, a long while ago, so more than a decade, almost 2 decades ago, ENEN started its support, how should I put it, its actions towards improving this knowledge in the nuclear field. So today we are facing one of these actions. We are facing a nice action which in principle should have been in presence, but unfortunately due to this COVID situation we cannot do it in presence. I remember a couple of years ago it was very, very nicely done by our colleagues from Hungary, and it was an exceptional meeting during that time. Again, I would like to congratulate everybody who entered the summer school, and I hope that you will enjoy this period together. Good luck, everybody. Thank you.
Okay, thank you, Gabriel. Leon, you also wanted to say hello.
Yes, thank you. And I also wanted to share with you a few slides, and I hope this will work for me. Does it work? I hope it works.
Yeah, we can see it.
I would just like to welcome you all at this very important event. I also share a little bit of sadness that we cannot meet in person in beautiful Budapest like it was planned at the beginning of the project. I hope we'll be able to compensate for this in the near future, and I hope to meet at least some of you at some occasion which will develop hopefully maybe by the end of the summer. We'll see. Anyhow, let me just give you just some very, very basic information about the ENEN Plus project, which is actually supporting this event and would also support the event in Budapest, if that would be possible. Gabi already mentioned that it's devoted to attracting, retaining, and developing new nuclear talents, of course, in the nuclear professions. And it is at the moment 4-year project with total cost of about a little bit more above 3 million euros, where European Commission is contributing 2.9 million, and it unites in a way 4 different nuclear disciplines. That's probably one of the first projects really doing this in such a setting. So nuclear engineering and safety is one of the disciplines. Another one is waste management and geological disposal. Then it's medical applications. I will go that way. And radiation protection. Radiation protection is something all of the others are using in a way. Let me just say again, it's to attract, to retain, to develop, involve, of course, all nuclear stakeholders and sustain attraction, retaining, and development of the pipeline of human talents in the nuclear, in different nuclear industries. You may see that there was out of the budget, roughly 1 million was devoted to the mobility of the students. And among the partners, you can see industry, Westinghouse, Technotom, French utility, EDF, operating all French power stations, And then you have some research institute like Czech CVR, Czech Research Institute in Rzesz, SEK-SEN in Belgium, and Josef Stefan Institute in Ljubljana, Slovenia, a bunch of universities and a bunch of international organizations like ENS. Thank you, ENS, for being here, Kirsten and Mattia today with us and helping us very much. And then it's Foratom, it's Industrial Association of Nuclear Industries, Nuclear Power Industries, EFOMP, Federation of Medical Physicists, and Nugenia also. Nugenia is part of the Sustainable Nuclear Energy Technology Platform operating in Brussels also in research. So without further ado, I'll just show you some selected results of the projects which will perhaps help you. There is attractive information about nuclear professions which are available from the websites of ENEN Plus and also from the summer school. And then very first, the basic information about the mobility program. So with a little bit less than 1 million euros we had in our budget, we were able to move in these 4 years nearly 500 people. Altogether, this goes nearly to 16,000 person days in mobility, which is, by the way, if you calculate a little bit, about 44 person years. So young people, nearly 500 of them had altogether 44 years of experience. And you can see that this is the countries of origin. So not only Europeans, but mostly Europeans. There were some from Brazil, some from Mexico, some from United States, and also somebody from Pakistan. And they were going to not only Europe again, but to many countries, including Argentina and Canada and Australia, China, also Russia, of course, and Japan. So the most of them nevertheless went to Germany. That's not because the German nuclear policy, but because there is a joint research center of European Commission has a nice laboratory for nuclear materials in Karlsruhe, and that's the reason a lot of people went to Germany. With this, let me welcome you and wish you a successful week. Let me repeat one of the things I said to one of the groups. Ask questions, as many questions as you can. It's probably a good opportunity to satisfy your curiosity, not our ambitions to talk. You know, professors, we talk when they say, ask us to talk, we talk, that's okay. But you should stop us and ask the questions. Thank you.
Well, I have to say, yes, it was very short. Was a very short presentation, nice and to the point. So, are there any questions? I saw one question which has been answered. It's about the number of the budget. Mattia, what do you propose should be next? You're talking about the next presentation.
Yes, I suggest to start with presentation as it will be a bit longer than the time schedule for each lecture. So if you are okay, we should start with the presentation of Professor Attila Jodi about the nuclear energy. I can start sharing the video when we are ready.
Yeah, wait, okay, we'll do this. Let's first see whether there are more questions.
Yeah, there are some questions.
I read a question here. Can you please provide examples of mobility programs? Leon, I think the question is best for you. You want to take it?
Yeah, unfortunately, only for the already done mobility programs. So we had kind of I tend to say individual programs. So we supported students who arranged their own missions. So we were not really matchmaking between what students wish and what is available, but we ask students to find an internship or exchange in the school or the doctoral or postdoctoral research projects, and then we supported them those who proposed the best programs, we supported those. Not unfortunately, not everybody could get the money, but actually, I think the probability of getting the money was roughly 75 or so percent. So it was rather high. At this moment, the program is not running. We are applying or considering application for the next call. So we could probably reopen with a little bit of luck the program in the beginning of 22, but at the moment this does not work. The only working program for nuclear students at the moment, to my knowledge, is Marie Curie, which is opening call now, and it's specialized for I think PhDs and postdocs, not for masters and not for bachelors. We had bachelors, masters, and also lifelong learning inside of the ENEN Plus, and we hope to have it also in the next in 22 to restart that in 22.
Okay, so if I understand well, so the process is that, I mean, the Commission has these framework programs where they have, well, some money dedicated for certain things, but you have to apply for these to be part of the program and to be able to run your project as you're proposing to the European Commission, no?
Yes, that's correct. And the call is out now. The results and start of the project will be early next year.
Okay, so we'll know more about it early next year.
Yep.
Okay, and I also saw that some people were going to for example, Argentina. So if a European student proposes a very interesting project in Argentina, there are possibilities to get supported for this program as well.
Yes, absolutely. At least it was so in the ENEN Plus project. I think we'll also propose this for the next project. Like I said, it was completely individual. So if a student found something in Argentina, and Argentina, by the way, is pretty lively nuclear, at least nuclear power country. So we supported them to go there.
Okay, thank you very much, Leon. Is there any other question?
Kirsten, I would like to add something here. So except for this project that is going to reach its end really soon, in fact in September, ENEN has also some other projects which some of them can have this support for mobilities. Unfortunately, the big difference between these projects and the ENEN Plus was, or still is, the fact that ENEN Plus supported a broad range of nuclear topics. The rest of the topics that can be found on the ENEN website have dedicated, so targeted actions. So, for example, I'm just giving an example now. If you have some activities, or if you are involved, or if you are looking for an activity or a program in the nuclear radiochemistry, there is currently a project, the SINCH project, which still offers some funding to go to activities developed in the project. So you might find some support, but again, this was not at the level of the former ENEN Plus project.
Okay, thanks a lot, Gabi, for this interesting information. I have a question here. What exactly is supported by these mobility funds? Is it only the travel, or is it a monthly allowance, or how does it work exactly?
Yes, it was travel. There was a fixed amount, I think about 500 euros for the travel. And there was kind of daily allowance, which was a little bit dependent on the length of the stay. So it was larger for shorter stays and smaller for longer stays. If you go for a year, I think the longest stay was roughly 18 months. So if you go for 18 months, you find a cheaper stay or cheaper accommodation than if you go for a week. And for lifelong learners, there was also support towards the fee for the course. If there was a course, it was which was good for the career of the specific people. There was a support to pay at least part of the fee. All these amounts were limited, so we were probably not always providing the people all the money, but definitely if you get maybe let's say 100 euros per day for a few 2 or 3 weeks trip, that's okay. You can survive on that. And the money was actually given upfront, and luckily we had an agreement with the European Commission that we did really not have to provide receipts. It was you have a lump sum for the travel, so you can arrange your travel with this lump sum, which is calculated based on the number of days where you go. So that was the part of it. So all the costs of the other, like insurance and maybe salaries for PhDs, and so that was not the part of the mobility support. That had to be taken over by the sending or receiving organizations, and it was.
So it's really a support for getting out of your hometown, yes, or where you are at the moment, and to move somewhere else to be at a different place. Yep. Then.
And we, sorry if I just add this one, we counted on the fact, and it worked, I think, nicely. If you bring to your boss the information that a quite substantial part of your mobility is paid, then they usually put a small amount of money in addition to that and let you go. That was, or your parents or somebody else. Everybody is kind of happy to try to support if there is, let's say, 70 or 80% of money already there. Thank you.
Okay. Kirsten, can I say something?
Yes.
I think I would like, first of all, to thank the ENEN consortium for this project. I think this was, in my opinion, a fantastic opportunity. Okay, a fantastic opportunity for students, and even I can see from my own young medical physicist. Medical physics is a very young profession in Malta, and the opportunities that ENEN provided to the young medical physicists to move out of the island and go to institutes which have a very high level of medical physics, and which they can then bring the experience here back to Malta. I think it was super. I am actually praying a lot, even though I'm not actually a super believer, but I'm really praying a lot that ENEN will be again successful in getting money from the EU, because I think this was something which I wish I had when I was young. Let's put it this way: this type of opportunity. And I think, and secondly, I would thank tell the young people, guys, sometimes we live in a world, you have grown up in a world where the emphasis on study and working hard is sometimes becoming too low. You have a lot of things which are competing for your attention. Okay, the internet has become very powerful, but not just for study, but for many other things. You have a lot of commercial things trying to attract you away from your studies. I think this is sometimes it's a pity, because you have so many opportunities and not so many people make use of them. And this is, in my opinion, a very big contradiction in the modern world, that young people today have so many more opportunities than we had when we were young, and yet not so many students are ready to take those opportunities. Many of them want to work in summer, and they end up the whole 3 months at McDonald's, okay, which is okay, they make some money, but do you really enrich your life? Okay, and remember, you have only one life. Make it as rich as possible. Don't spend 3 months pushing burgers, please. I mean, there is more to life than this. Huh? Thank you.
Okay, thanks. I actually have a question, Leon. Maybe the next program will not be the same as this one, but who can apply? Is it bachelor students already? Is it master? Is it PhD? Can you, if you already just entered your professional life, can you also apply this?
Actually, it was meant for bachelors and up, so bachelors were welcome to apply. Of course, the activities, supported activities of bachelors were different. So we supported internships and to some extent study exchange. I think that was more in masters already. So for masters, there was an idea that if they go for a few weeks or months to another university, or maybe even a semester, that was a limiting case. There was some limited support for that available. And then, of course, for PhDs and up, it was a few weeks or few months of research projects at some infrastructures or some other teams where it was possible to do some experiments which were not possible at home. And as Carmel nicely said, we had quite a lot of lifelong learners. That was the group we called it. So professional trainings. So when you're a young professional, you come into your workplace. We also supported those to get to certain courses, exchanges, which could improve their careers. That was a kind of highlight. So that was the way how we evaluated the proposals. If we believed that this action will improve the nuclear career of the person applying, then that was the reason to support it. Let me just add one more thought to what Carmel put so nicely. It's actually, for young people, it's very important that you find your let's say professional friends. Some people call it networking. As if you know a lot of people around, not only in your country but also everywhere else, especially in the different centers of professional interest, that will help you immensely in your career. So I would really strongly suggest you try to do that. Work with people in different cultures and different countries, and you will be much richer in your views of the world, and in your professional success will be easier. Thank you.
Okay, yeah, thanks. I think it's yeah, I mean, working in a very international environment, I think we can also agree with this. So it's very, very enriching. Yeah. Okay, I guess if there are, if somebody of you, the young students, are interested in participating, maybe not now, but maybe it's because it's only in 2 years or in a year and a half. I think ENEN is always there. You can always pop a question to ENEN, or I mean, Leon, I guess, will always be linked to ENEN as well, and Gabi is there as the general manager of ENEN. So just ask them a question, or yeah. I guess we also keep this mailing list as the students of this year, and launch you once the program has gone through, if it goes through. Okay, so we are ready, I think, now to jump to the next session of our program, which will be, now we'll have 2 presentations, one about nuclear energy and then about radioactive waste management. Then we have a break. And then Carmel will talk about medical physics, and then we have another talk about radiation protection. So 2 talks, a break, and then another 2 talks. And I turn to Mattia because the first talk, unfortunately, Dr. Attila Azotti, he is not able to join us now.
Yes.
So it will be a presentation on screen.
Here I am.
Okay, and we see it's a bit longer than 30 minutes. It's 43 minutes.
My name is Attila Azotti. I am professor at the Technical University Budapest, Hungary. I would like to welcome you here in this virtual session. I am very sorry that you cannot be present in Budapest during this ENEN Plus event. However, I am very happy that even in this case, during this very strange COVID pandemic, we can organize the ENEN summer school, and I hope that you will learn a lot in this form as well. My task is today to speak about nuclear energy, and not only about the energy production in nuclear power plants, but also the role of nuclear energy in the continuous and climate-friendly electricity supply. Let me start with the definition of energy, and with a short description. What do we do we use energy? So in general terms, in physics, the energy is the ability to change something. If we want to move something from a point to another one, or if we want to change the physical state of a material, we need energy. In fact, nowadays, all the industrial processes, everything in the society requires energy, and for that purpose, we need continuous supply of energy. We can say that energy and the energy supply is in fact an inevitable part of our life. We cannot imagine the life without the continuous energy supply. However, there are drawbacks of the energy supply as well. Most of the energy production processes have environmental consequences, environmental pollution, or the possibility to pollution, and definitely saving the environment and decreasing the environmental consequences is one of the major objectives of the mankind nowadays. If we are speaking about energy, we have to clarify that energy is not equal to electricity. So energy is used in many processes, really, for power production, but also for transportation, agriculture, industrial manufacturing, a lot of services, households, buildings. They are reliant on energy. They require energy for the continuous work, and we supply the energy not only in the form of electricity, but for example, by natural gas supply or district heating, and hydrocarbons for transportation and so on. Today, I would like to concentrate on the electricity supply and on the electricity production, because you will see later on that electricity is a form of energy which is very widely used, and it is universal. It can be converted to any form of other energies, and therefore the role of electricity supply and the role of electricity is increasing continuously nowadays. So today we will concentrate. Let me use the highlighter. So we will speak mainly about the power production and the different ways for power production. If you look at this chart, you see that in the last 50 years, we can observe a continuous growth in the global electricity generation, because the need for electricity is continuously increasing. There are only few exceptions, mainly the periods of big global recessions, economic crises, in which we can see some stagnation, or in some cases some decrease in the electricity needs, and this is clearly true for the COVID times. In 2020, in many countries, the electricity need decreased because of the shutdown of the industries during the first wave of COVID pandemic. But after the first shocks, we could observe a further increase in the electricity needs and the electricity generation. You see in this figure also that most of the electricity is produced based on fossil energy sources in fossil thermal power plants. And I will describe later on what is the situation in Europe. We clearly expect that the need for electricity will will be increasing in the future as well. You can imagine that IT equipment, manufacturing, household appliances, electrical cars, they all need electricity, and we are using those equipments more and more nowadays. Therefore, we expect that in the developed world and also in developing countries, the need for electricity will be increasing in the next years and the next decades. Please consider that for e-mobility, if we want to use e-mobility to make the air cleaner, and if we want to use e-mobility to decrease air pollution and emission to the atmosphere, we need those electricity sources which are not reliant on carbon. Therefore, in fact, e-mobility will be climate friendly only if the electricity used for charging the batteries in electric cars will be produced in nuclear power plants or in hydro, wind, or solar power plants. So we have to move the electricity sector towards those zero emission or low carbon technologies from the current mainly fossil-based power production. Just to summarize, I believe that the world in the developed countries and also in the developing countries will require more electricity in the future. The role of the electricity will be increasing. And the key element is if we can supply this electricity based on low carbon or carbon-free technologies like nuclear or renewables. Here in this figure, you can see the different electricity production technologies and the CO2 emission, the specific CO2 emission. You see that the lowest CO2 emission can be observed by solar PV, biomass, nuclear, hydropower, and wind energy. If we consider the whole life cycle of a power plant, these values are not zero. It doesn't mean that running a wind or a nuclear power plant will produce CO2. But once again, if we consider the whole life cycle from the construction until the decommissioning of the plant, and if we consider also maintenance and all the necessary processes during the life cycle of the power plant, we will have certain CO2 emission in all those technologies, but clearly solar, biomass, nuclear, hydropower, and wind are those technologies which have the lowest life cycle CO2 emission. And if you compare those values to lignite, coal, or natural gas, you see that 2 or 3 order of magnitude higher CO2 emission can be observed for the fossil based power plants compared to the low carbon technologies. So for the climate protection, we definitely need those low carbon technologies. The question is, how can we integrate those power plants into the electricity system in order to have a stable and continuous supply of electricity, because this property, the continuous supply, is a key requirement in the nowadays electricity systems. So let's speak about the nuclear power and let's see what is the role of nuclear power today. First of all, I just want to show you a few slides on the nuclear power plants and the basic functioning of the nuclear power plants. If we compare a nuclear power plant to a conventional power plant, for example, to a coal-fired power plant, the basic physics processes are very similar. We produce steam in order to drive a turbine, and the turbine drives the generator, which produces the electricity. So both coal-fired power plants and nuclear power plants are thermal power plants based on Rankine cycle. However, the big difference is that in nuclear power plants, the heat which is used for the production of steam is produced in the reactor, which doesn't require any CO2 emission to the environment during the operation. The other big difference compared to coal-fired power plants is that the energy density of nuclear fuel is much higher, 6 orders of magnitude higher compared to coal or natural gas. 6 orders of magnitude means 1 million times higher energy density can be observed in a nuclear reactor. Therefore, the reactors are a very concentrated source of energy. And we can run this kind of power plants for 1 or 1.5 years without reloading of the fuel, without any intervention in the reactor. This is very important because for a coal-fired power plant or a gas-fired power plant, you need continuous supply of fuel. It is not the case in the nuclear reactors. If we once load the fuel to this reactor, we can really run the reactor for 1 or 1.5 years without reloading the fuel. This is important because of the security of supply. So if you have the stock of nuclear fuel, you do not need to continuously import or continuously produce the fuel because of that high energy density. In that figure, you see the basic scheme of a pressurized water reactor. Pressurized water reactor means that we have 2 different circuits in the power plant. In the so-called primary circuit, the pressure is high enough to keep the cooling water without boiling. So to keep the cooling water in fluid state. In the secondary circuit, the pressure is lower. There is a thermal link between the primary and the secondary circuit, and this thermal link, this coupling, is in the so-called steam generator. So in this steam generator, we turn the heat coming from the reactor to produce steam, and this steam is driving the turbine, which is driving the generator, which produces the electricity. What is needed, it is extremely important in case of any thermal power plants. So what is needed is the condensation of the low pressure, low temperature steam coming out from the turbine. For that condenser, we need some cooling water from the sea or from a river. So for the running of a nuclear power plant or any thermal power plant, a large source of cooling water is necessary. Therefore, all thermal power plants, including nuclear power plants, are located close to a river or to the sea. And in fact, during normal operation, this is the only environmental effect of a nuclear power plant, the heat load to this river or sea, because all the waste produced during the reaction is kept within the fuel. Therefore, in your normal operation, there is no other environmental consequences except the heat load to the environment. You can read the name of the main equipment. I don't want to explain all the details here. The other major type of nuclear reactors is the so-called boiling water reactor. It is simpler from the point of view of the thermal cycle. You can see here that in the reactor core, the water is boiling, so the steam is being produced directly in the reactor core, and the steam phase is separated from the fluid state, and the steam is going to the turbine. So this is a simpler cycle compared to the pressurized water reactors. However, it has some disadvantages because the water, the cooling water of the reactor always contains some radioactivity. In the case of boiling water reactors, this radioactivity is going to the turbine, so the turbine is also contaminated, and some part or partially the whole cycle, turbine cycle, is contaminated weakly with radioactive materials, contrary to the pressurized water reactor, in which the secondary side, so this turbine cycle, is totally free of radioactivity. The cooling need is present here in the boiling water reactors as well. Regarding the technologies, you will learn more during this summer course, or if you are interested in, you can find a lot of textbooks on that technology. Let me come back to the energy perspective, and here I listed some characteristics of nuclear power, some advantages and disadvantages, what we can consider if a country is considering the construction and operation of a nuclear reactor. So first of all, I have to mention that the nuclear power has a very important advantage, namely that it is a large concentrated power source. It means that if we construct 1 or 2 units, this will add 1,000 or even more megawatts to the electricity grid. So by constructing a few units, you can increase the installed capacity in the system very quickly because of this large concentrated power source. On the other hand, these reactors are quite complicated. So for example, for load following, they are not so easy to manage. But with appropriate technical measures, clearly the load following in the modern state-of-the-art reactors is possible as well. A big advantage of nuclear power is, as I mentioned before, that it is a CO2-free source of electricity. So we do not produce any CO2 during the operation of the reactors. And as I mentioned before, even for the whole life cycle, the specific CO2 emission of the technology is between the lowest. So for climate protection, definitely nuclear power is a very good power source. As I mentioned, by the describing of the different power plant technologies, the only effect environmental effect of a power plant, of a nuclear power plant, is the heat load to the environment, or the heat load to the river or sea close to the power plant, which is served as cooling fluid. But this can be managed, and this is not something which would harm the environment. The next advantage of a nuclear power plant is the high availability. So typically 80–90% of the year the nuclear power plant can run and produce electricity by 100% of its nominal power. It is this high availability, this 80–90% or even higher than 90% is really high compared to solar, for example, which has maybe 15% availability, or wind power, which has approximately 25 or 30%, dependent on the site in which the wind power plant is installed. So compared to those technologies, nuclear has very high availability, and it means that it can really serve as a base load source of electricity. We have to mention that nuclear power plants are big and complicated because of the safety measures. A lot of safety systems are required, so the licensing is complicated in many cases. Therefore, the cost, the installation cost or the construction cost, the so-called capital cost of nuclear power, is quite high. On the other side, the operational costs are very low. So the main cost driver is the fuel, the uranium-based fuel, but this is one of the cheapest sources of energy. So therefore, running a nuclear power plant requires low operational costs. On the other side, once again, the construction costs and therefore the capital costs are high, but we can run really nuclear power plants with high availability. Therefore, the production of electricity in a nuclear power plant can be competitive and can definitely compete with natural gas or also with renewable sources. Nuclear power plants have long operational time. Typically, the current reactors have been designed for 30–40 years, but they are capable for lifetime extension. So the current reactors are planned to run in 40, 50, 60 years, and the new so-called generation 3 reactors will run definitely for 60+ years, maybe 80 years. So this long operational time is a very important advantage of the nuclear reactors compared to solar PV, for example, for which the average lifetime is approximately 20 or 25 years, or for wind, which is 25–30 years. The 60+ years operational time of the nuclear reactor is really long, and therefore this compensates the high investment and capital costs that I mentioned before. As the last advantage and disadvantage, I have to mention the waste question. So I think this is a very important advantage of nuclear power, that the waste is concentrated. So in fact, all the waste is kept in the spent fuel, which is in the core, and later on loaded from the core. it is definitely an advantage that the waste is not dispersed to the environment. This is concentrated. However, on the other side, we have to deal with that concentrated waste, and it complicates the public acceptance of a nuclear reactor. So safety and the waste and the safety of the waste is a key element which has to be designed in advance, so the public can accept. In many countries, nuclear is in the focus of politics, not only in energy policy, but in other aspects of policy. So the established communication strategy, information to the public is extremely important to keep the high acceptance of nuclear power by the public. Let's see some figures regarding the current status of nuclear power and the current role of nuclear power. So you can see that the current fleet of the nuclear reactors has been developed in the 80s, 90s mainly. So the fleet what we have nowadays was constructed in the 70s, 80s, and 90s. In Hungary, in the country where I am living, the share of nuclear power in the electricity supply is more than 1/3, so 36%. In the European Union, this number is 22%, and worldwide it is more than 10%. So nuclear power is once again the most important carbon-free baseload source of electricity. Those power plants are running continuously and give the basis for the safe operation of the electricity system. You can see here those main sites in which nuclear reactors are in operation. You see these blue signs, which are the pressurized water reactor sites. The greens are the boiling water reactors, and the red are some other type of reactors in operation. Today, more than 440 reactors are in operation. I mean power reactors, not research reactors, but power reactors, and more than 50 reactors are under construction. Most of the current nuclear capacities are based on the pressurized water reactor technology. So you see that the number of reactors, the number of pressurized water reactors is close to 300, and the total installed net capacity of pressurized water reactors is more than 280,000 megawatts, so more than 280 gigawatts. So the second largest installed capacity is based on boiling water reactors. PHWR reactors are the heavy water moderated reactors, and you see here still light water graphite moderated reactors in operation, gas-cooled reactors, and fast breeder reactors. I mentioned previously the high availability factor of nuclear reactors. You see here in this figure that it is really the world average is above 80%. This decrease, what you see here, is because of the Fukushima accident. You know that after the 2011 Fukushima accident, in Japan, but also in other countries, the the operation of many reactors has been suspended, and this is the effect what you can see in the energy availability factor. Here are the countries which are running nuclear power plants. So you see that in France, the share of nuclear energy in the electricity production is over 70%. And in other countries like Ukraine, Slovakia, Hungary, Belgium, Bulgaria, it is close to 40 or even higher than 40%. I don't want to list all the countries shown in this figure, but you can see here the 30+ countries which are using nuclear power nowadays. Regarding the current fleet, this figure is very interesting and important. You can see that most of the current operating reactors are 35 years old. As I mentioned previously, the design lifetime of those reactors with lifetime extension is 50 to 60 years. So it means that those reactors will run in the next 25 years. However, we will need further new capacities, and some new capacities are coming. On which technology and in which regions and in which countries, you can see here the answer to this question. So I have to outline that the most common technology for the new reactors, for the reactors under construction, is still the pressurized water reactor technology. Most of the new build projects are based on large pressurized water reactors, and I think in the next 20 years, the pressurized water reactors will be the leaders in the nuclear developments in the new build projects. Where those reactors are being constructed, you see here that mainly Asia is leading that market. So China, Korea are constructing or have been constructing a lot of new reactors, but also in Europe, there are new build projects on the way. In Hungary, we have the PAX-2 project. In Finland, we have the Olkiluoto 3 project, the Hanhikivi project also in Finland. In France, the Flamanville 3 project, but Czech Republic, Slovakia, Poland, Slovenia considers reactor construction for power production. Let me finish my presentation with some perspective regarding the European electricity mix and the European power market. In the European countries, in the European Union, in 2018, this is the last year for which I have official data currently. So based on the ENTSO-E data, you can see that 41% of the electricity has been produced based on fossil fuel, 35% based on renewable sources, and 22% based on nuclear power, as I mentioned previously. What were the main technologies in that graph? So for the renewable sources, I have to mention that not solar and wind are the leading technologies. You see in that figure that hydro is the most relevant or most important source of renewable electricity nowadays in Europe. Wind and solar is increasing, but still hydro is the largest source of renewable electricity in Europe. Regarding the fossil sources, natural gas plays the most important role. However, if we add the lignite and the hard coal, those two columns in this figure, you can see that they play also very important role. So if you add hard coal and lignite, you will get approximately the same figure like for natural gas. It is important because once again, if you come back to that figure, you see that in Europe, more than 40% of the electricity is produced based on fossil, and because of the climate protection goals, we have to switch from those electricity sources to others which are carbon free or low carbon technologies. The different countries have very different power plant system and very different possibilities for electricity production. You can see that countries like Austria is reliant more than 60% on renewable. It is mainly hydro, not wind and solar. Other countries have major nuclear production capacities like Hungary, France, as I mentioned before, but other countries. But if you see the main color in this figure, you will see this yellow, which is the fossil. So switching from CO2 emitting technologies to low carbon technologies, here there are a lot of challenges for most of the European countries, and a lot of developments will be necessary in Europe to have a new electricity system which is much less reliant on fossil. By designing the new electricity system, we have to understand, however, that base load is necessary. So you can see here 2 days, the load curve of 2 days in Europe. You see the one is from 2018 February, the other one is 2018 June. So you can see from the figure that we need electricity during all day and night. We definitely need a base load electricity sources because many electrical systems or many electrical appliances are running continuously. So we cannot serve all those needs only with wind and solar. Therefore, we definitely need like nuclear power plants, which can run with high load factor and which can run during day and night during the whole year, except the very short period of maintenance and refueling. As I mentioned previously, the different European countries have different electricity systems, and the CO2 emission is very different in different countries. I would like to recommend you to visit this electricitymap.org website, in which you can follow how the different countries are operating in the current state, and you can see what is the specific CO2 emission of the specific country in the current state. So you see here that, for example, Poland, Turkey, or Germany or Czech Republic is reliant much more on fossil than, for example, France or Norway or Sweden, in which the combination of nuclear and renewables can give a much lower specific CO2 emission. Just to summarize my presentation, I would like to mention that, in my view, there are very important changes in the electricity supply of the world and also in Europe. So we are switching from a fossil reliant electricity system to a carbon neutral or low carbon electricity system. In that power system, nuclear power plants and renewables have to cooperate. They have to work together and ensure security of supply and the continuous supply of electricity, because electricity is the form of energy which is most widely used nowadays. And as I mentioned in my presentation, the role of electricity will be increasing even in the future. By constructing new reactors, we have to keep nuclear safety on the highest level, and we have to keep the public acceptance of nuclear power, because political support and without public acceptance, nuclear cannot be sustainable. But we need a sustainable electricity system, and we need sustainable nuclear energy. Thank you very much for your attention, and I do hope that you will enjoy this ENEN Plus summer school in year 2021. See you next time. Bye-bye.
Okay, so this was Attila's presentation, who unfortunately couldn't be with us today. Well, we're running a bit over time, but I think it's really important to have some interaction, and I really will thank everybody who's active in the chat. I saw that there's some interaction. Actually, there has been some exchanges about uranium supply. So we all know that there's a lot of discussion about oil, whether that the oil supply will be enough and for how many years it will still last. And there's some discussions also about the uranium supply. So I saw that Marian is already answering the questions. I don't know, Leon, are you here still with us? Let me see, Leon.
Sure.
Leon, you also want to say some words about this, about the uranium supply. How long will it last? What's going on with the uranium supply? What's the situation?
Well, thank you for this question. As far as I understand, there is, like usually, it's more the question of price than question of quantities. At this time, what I understand is that we are probably we are very good for at least 200 years with what we do today. And one of the interesting technologies for uranium supplies, which has been just recently patented, is to extract it from the seawater. And if we can do it from the seawater is leaching the geological structures around. Then we can go far beyond the 200 years. And if we are using also the uranium-238, not only 235 for the chain reactions, then we are probably approaching something like 2000 years of supply, which is actually much more than what's known for the oil. Although also for the oil, at least in the years I'm following this, I believe that we started to be afraid in the 70s that it will run out, but since then we are still discovering much more new sources than we are using. At the end of the day, we are not very close to the shortage of oil today, as far as I understand.
Okay, thanks. Marian, you want to present yourself and maybe also react directly with your voice? I saw you already put some comments in the chat.
Greetings, everyone. I am speaking to you from the United Arab Emirates. And regarding the question, I obviously did a Google search for the uranium supply. And from my understanding is that uranium is not in danger of being, let's say, consumed within this lifetime. So for our generation, I feel that we are covered. The only thing that we need to do is build more power plants, so then we can really challenge the supply of the uranium that's being extracted right now.
Okay, thank you. Any more comments, questions?
Just to give you an information, because the reserve in the earth of uranium is about 12 million tons today. But as Leon said, there are 5 times more in the water, in the seawater, uranium in the seawater than in the air. So there is no doubt that we can go very far with this quantity.
Okay, thanks.
May I just make a comment?
Carmel, yeah, go ahead.
I think the question of that the Earth's resources being depleted, I think it's not really a strong argument. I mean, the Earth is so big. We only perhaps have dug a few kilometers in the Earth's crust. Remember, the Earth is really big. I think it's not a question of resources. I mean, even oil, there's a lot, and they're discovering it every year. They discover more oil field. I think the question is the pollution. I think this is the most important, in my opinion, question of our day. We can't keep on burning fossil fuels, and they end up in the atmosphere, and it's the air pollution, in my opinion, is the worst thing. We're breathing this thing. I mean, you go to these big cities, you measure the pollution level, and you say, "My God, I don't want to live here." I mean, I was in Beijing some years ago. I mean, when we went down from the plane, I mean, you could. The air pollution was unbelievable. I mean, it's you're breathing it all the time. I think this is the biggest issue that will face this generation and the next generation, the air pollution, because it's affecting even the babies that are born. Okay, why all these increases, for example, in autistic children? Why all the increases in cancer? I mean, there are statistics for these, so they are increasing. It's the pollution. So if nuclear energy can be, we can convince the people out there that nuclear energy, we can forget about what happened in Chernobyl after we analyze why it's happened, so that never happens again, and convince people and of its safety. I think it's the only way forward, in my opinion, to reduce the pollution. Okay, we have solar energy, we have wind energy, but you'll never get the amount of power you need. In Malta, we have a lot of sun. Okay, we have produced a lot of solar energy, but it will never power all our houses, our industries. It's not possible.
Okay, thank you very much. Beirut, you're touching another very interesting subject of nuclear waste management.
Yes,
please go ahead.
To share my screen, if I can.
Yeah.
Okay, you can see my screen?
Yes.
Okay.
Okay, go ahead.
So I try to put that in full. Okay. Okay, may I start?
Yeah, you're ready to go.
Okay, hello everybody. So my name is Behruz Bazargan-Sabet. I'm professor at Université de Lorraine in France, and I'm also member of the French regulatory body for the nuclear activities in France. So today I will try to give you, let's say, some flavor about the radioactive waste, the problems and the solution that we have for. Indeed, the subject is very, very large, but I try just to give you a kind of overview of different aspects. The first things is that you must know that any activity related to the nuclear, will be production or use of radioactive materials generate radioactive waste. So in this image, you can see at the left side, top left, an application in medicines, for instance, application of the radioactivity in medicines. In the right hand, you have an application about the dating. Here is rock art, the dating of the rock art. We use generally carbon-14, which is a radioactive material for that. There are many industrial use of radioactive materials, radioactive energy. And one of them is shown here in the left side, left down. This is a control of the welding in a very long pipe. You know that the welding must be perfect in order to avoid any seepage of the gas or even liquid during the transport. And as you have kilometers of pipe over the world, it is very important to have a very good welding. And the way to control that is using here a gamma ray source and to have an image of the welding part of the pipe. And here in the right bottom side, you have another application in agriculture. This is about the germing of agriculture products, using also gamma ray mainly. Other applications could be found in the space, and of course, production of energy through reactors, through nuclear reactors. So the management of radiation emitting radioactive material is a matter of concern, and it's make the nuclear waste apart. Public acceptance of the nuclear energy is largely depend on the public assurance for safe management of the radioactive waste. So as the discussion before, this public acceptance is the basis of the development of nuclear in general, and this is very important. In the nuclear waste is a very important part in this decision, in let's say the education of the general public on that. Knowing that not all nuclear wastes are particularly hazardous or difficult to manage, as compared to other toxic industrial waste. The part of the really dangerous material in this waste is less than 0.5%. So the quantity is very very low, and talking about the total quantity of the waste produced through the nuclear application regarding to the others, this is less, all the nuclear waste together is less than 1% of the waste generated in the world. So finally, the high level waste, the very dangerous part of this level waste is less than 0.05%. It's a very, very small quantity. However, in accordance with the international guidelines, radioactive waste must be managed in the manner so as not to cause any radiation risk to the public and to the environment. So the management of this waste cover a very broad range of activities, going from the handling of the waste, the treatment, the conditionings, up to the transport, storage, and disposal. There is difference between the storage and disposal. The storage is an interim operation, is the activities that consists to put the waste somewhere waiting for the final disposal. So this is the difference between the storage and disposal. Radioactive waste can be different form. It can be in gas, liquid, or solid form, and its level of radioactivity can vary. The waste can remain radioactive for a few hours or several months or even hundreds, thousand years. Depending on the level and the nature of the radioactivities, radioactive waste can be classified according to this matrix here. So here you have the lifetime of the waste that could be short, medium, or long. And in the x-axis, you have the activity that could be low, medium, or high. So you can find any kind of radioactive waste in this matrix. For instance, you can have long life waste with low radioactivity here, as you can have here, for instance, a medium life material with very high activities. I will show you a little bit further another way of classification, which is the international classification of this material. Okay, so the most part of the radioactive waste, let's say more than 98%, is generated during different operation of so-called the nuclear fuel cycle. What is the nuclear fuel cycle? It's all the activities, all the operation that is linked with the production of the of energy in the power plant. So this consists in activity beginning by mining, the processing of the uranium ore, the conversion of this ore to the gas, and the enrichment of the uranium, then the fuel fabrication, then we go to the power front from burning this fuel. This will produce some waste that could be stored as it is directly from coming from the reactor, or can be reprocessed and recycled. Means that part of this waste can be recovered and used for the fabrication of new fuel here in the facilities. And in this reprocessing activities, we produce the so-called high-level waste, which is about 5% of this spent fuel originally coming from the burning of the fuel in the reactor. Let me show you the occurrence of the uranium over the world. So the uranium is, let's say, rather well distributed over the world, and the quantities is about 8 parts per million of the Earth crust. As I told you before, the Earth reserve of the uranium is evaluated now at 12 million tons of uranium ore. I show you here different type of uranium in the lines. So here the dark parts is the oxide, the uranium oxide. You can see here. So this is one kind of this material called davidite. This is the pitch blende. The pitch blende is probably the first uranium ore detected, and it's here a very nice uranium oxide here inside the ore. You can have other form of combination. For instance, the autunite here, and this yellow part is the uranium contained in such a. The keranitite is another form. It's in vanadinite, so and this can be found in USA or in India. Another form is the coffinite, which is mixed with silicate, and mainly in Canada and Brazil. So, okay, so all of those ore are mined let's say, a standard mining operation. This could be in a deep mine, for instance, underground mine here in India, or could be in open pit exploitation here in Australia, for instance, or this could be obtained through the solution mining, means that you will dig here wells, and from one well you inject in the ore layer a combination of sodium carbonate, bicarbonate, and sulfuric acid. You obtain there a solution which contains uranium, and then you can pump it through this channel to the surface. After the mining, you have to process the uranium, and this is called the milling product. During this milling product, you will obtain a called yellow cake, which is uranium oxide, U3O8. This yellow cake contains 99.3% of uranium-238 and only 0.7% of uranium-235. That is, this uranium U-235, which will be used, which will burn in the reactor. So to be used correctly in the reactor, we have to enrich this yellow cake with more uranium-235, and this enrichment brings the content in uranium-235 between 3 and 5%. And this enrichment is done first by changing the uranium oxide to uranium hexafluoride, which is a gas, UF6, and then by using a centrifuge, like a zip centrifuge here, you can separate the uranium-235 with uranium-238. Uranium-38 is slightly heavier, so it's go down, and the uranium-235 go up. So in this way, you can enrich your mix, and then the enriched gas will be transformed again to the solid, and this transformation give the dioxide of uranium, which is the material used for the fuel fabrication. So here you can see it's a powder. The powder is then transformed in the pellet, in ceramic pellet, and this pellet are put on the rod, and the rod is introduced in to the reactors. So you will see that all of those transformation and let's say applications produce waste, and this waste this stage is just stored as a standard mining waste, as you can see here in the right part, right side. All of this waste is put in the tailings, and so the problem is to be sure that these tailings do not produce, let's say, hazardous material for the environment. The first point that you have to well understand is that the uranium, and particularly the uranium-238, is not very radioactive. The radioactivity of uranium-238 is very low, but its lifetime is very, very long. So by itself, the trace of uranium-238 in this tailing do not produce major hazard. But the uranium is not the only materials containing in the tailing. Another radioactive material, which is usually present in the uranium mine, is the radium. And the radium, during its decay, produce a gas called radon. And this gas is, of course, radioactive, and as a gas can be seeped from the tailing and can go to the atmosphere. Other problem is that during the treatment of the ore, we will have to use other materials, other toxic materials, but not radioactive, like for instance arsenic. And arsenic can also seep outside of the tailing, and you can have seepage through the bottom of the tailings to the groundwater, for instance. How we deal with this hazard is very simple. We cover ore of the tailing with clay material. Clay has a very good properties in that they can fix radionuclide and radioactive materials. So with about 30 centimeters, even 30 centimeters of clay, it is enough to stop the migration of the radionuclide from the tailings to the environment. So this is very, very efficient way to close the uranium mining waste. Now, what happened inside the reactor? We have produced it, remember, we have produced this uranium, which will be the fuel inside our reactor. Inside the reactor, you have this reaction. A neutron can come and hit the nucleus of uranium and split it in two parts, ejecting some neutron during the reaction. It is important here to understand that material, this transformation can produce different materials, not just these one, but all the combination can be produced. The only let's say equilibrium that you have is that the mass number of these two parts produced plus the number of neutron produced must be equal to the mass number of uranium is 235 plus one neutron that you have to add to the system here for the fission. So if we consider what is inside the reactor, we have 4% of uranium-235 and 96% of uranium-238. During the fission of uranium-235, some products are created. This is called fission product. So 3% in average of this uranium-238 is burned for producing energy in the reactor. From the uranium-238 side, this uranium can capture one neutron and then one or several neutrons, will be transformed in plutonium. So 3% of plutonium is produced during the operation in the reactor, and some isotope of the plutonium react as the uranium-235. So they are fissile. This is about 2% of this 3% produced. So 2% of the plutonium inside the reactor will participate to the creation of energy and produce this fission product. So at the end of the operation, when all the fuel is burned, you have here in this blue box the so-called spent fuel. So the spent fuel is part of 5% of fission product, plus 1% of plutonium coming here, 1% of uranium coming here, and 93% of uranium-238, which is remained here. So this spent fuel can be reprocessed in order to separate this fission product, which can be produced as ultimate waste from this part, plutonium, uranium-235, and uranium-38, that can be again included to the production of the nuclear fuel. Now, what we continue with the radioactive waste coming from this power production. If we look at the different type of the waste produced in the reactor, we have this spent fuel that can be removed directly from the reactor about its useful life. We can have this high-level waste, which can be considered as ultimate waste, which is the residue of reprocessing of the spent fuel. This high-level waste here is a liquid in general, because the reprocessing of the spent fuel will create a liquid mainly based on the nitric acid. So this could be something that we have to discuss about a little bit after. The intermediate level waste, this is mainly coming from the parts inside of the reactor that could be contaminated by the radioactive materials, and also can come from the reprocessing. And finally, the low-level waste, which correspond to 90% of the volume of waste created in the reactor. So these low-level waste do not necessarily carry any radioactivity, or the radioactivity created by this low-level waste is under the level acceptable by the human body, for instance. So for this low-level waste, there are many different solutions for the disposal of this low-level waste. Here you can see example in USA where this low-level waste is just disposed in the desert in a very dry atmosphere, knowing that the altogether the activities and the life of this low-level materials is about a century. So it is more or less easy to control this material after disposal, even in the desert, like here in USA. In Germany, this is put in the mine, in the salt mine, and then will be recovered by the crushed salt. So it's also a way to dispose this waste. In France, the waste is disposed in a cell here, and when the cell is full, it will be covered with concrete. And here you can see the whole facilities. Here you have several facilities which is already full with the waste, and here you have the part waiting for receiving this low-level waste. Okay, so there are solutions for this low-level waste, for already safe solution for this type of
Yes. Sorry, Ruth, we are now running about 23 minutes late. I would say so if you take 7 more minutes, we should close the session at 4 o'clock and for a break. Yeah, 7 minutes.
I try to go faster. So the problem is with this high-level waste, which is highly radiotoxic and also produce some heat. And the problem is that this must be used for 10,000 or even million years. So the solution for this is to put the material in geological disposal at typically 500 meters depth. And this solution is consensus at the international level after about 40 years. So why this is the best solution? Because this is based on the scientific assessment of the risk. You probably know that the risk is a product of a hazard and a vulnerability. Hazard is about the danger, and the vulnerability is the susceptibility to the hazard. So the geological disposal is the solution that minimizes function risk regarding all the other possible solutions. Regarding the disposal of the spent fuel, this is a view of the spent fuel here inside the inside the containers. The canister here is made in steel, and put in other steel material called cask, and you can see the height of this assemblage. For the high level waste, as this is liquid, the treatment is to transform that in the glass by mixing this waste with the melt silicate, and you can see here this operation. And this glass here in the metal. So as I tell you before, the radioactive waste coming from the reactor produce heat. So during a period, you have to cool down these materials, and this is done in the just under the water, and this allows to reduce the heat generated by the waste. After this cooling time, the waste can be stored. This is interim storage, waiting for the final disposal. Today, there is no such a disposal, such a deep disposal. There is one under construction in Finland, and another one is expected in Sweden and then in France in around 2005. Okay, I just finished my presentation by saying that for the disposal, you need different barriers in order to be sure that the radionuclide cannot move to the atmosphere, to the biosphere. So those barriers are two types. Engineering barrier means man-made barrier, and the natural barrier, which is the rocks and the different geological layer over the I just skip this one. This is all the quality that you have to search for the storage for the site of disposal. So I just show you here different concept. This is the Belgian concept for the disposal. You can see here the canister and the different engineering barrier coming with the over packing material here, the buffer here, which is it. The yellow things here is a clay material. It's a bentonite, which has the possibility of swelling with water. And then you have the natural barrier here, which is the rock around. This is the Swedish and Finnish concept. Difference is just in the Swedish and the waste is disposed vertically and not horizontally. And this is the test of the Spanish concept, which. Okay, so I finished my here. Sorry to be a little bit faster at the end.
Well,
attention.
thank you very much, Beruth. Very interesting. Very interesting. I didn't consider, yes, there's front-end waste as well. Wondering about the radon and the radon caves in Austria, where you have to pay to go to the radon caves. But okay,
Yeah,
maybe
yeah,
that's another
but
discussion.
gradient is we have that. It is not just linked with the uranium production. It is also, for instance, you can find that in the iron mines. In France, for instance, the most radon is produced from the iron mines, and the other place that you can find that is in the granite. The granite produces radon, and if you go to Madrid, for instance, where you have a huge building in granite, many people are sick because they receive this radon from the granite.
Okay, Beruth, we have a lot of questions in the chat. There's an interesting discussion going on. But unfortunately, I think we really need a break. We're running half an hour late now, so I'm suggesting that we go on break for 15 minutes, so until a quarter past 4. But if you, Beruth, would go to the chat and just look at the chat and maybe answer the questions in writing in the chat, if you don't mind.
Okay.
Yeah.
Okay, I tried. If I found the chat, but I don't know where it is.
If you go to the bottom of your screen, you see the chat there. No, it should be on the bottom of your screen, a little chat bubble. Yeah. And for everybody else, I really suggest we break for until quarter past 4, and then we continue with Carmel. Okay. Yeah. See you soon.
Okay.
Okay, we're slowly getting ready. Carmen, are you ready? You're still muted.
I couldn't share my screen a minute ago. Let me check. Yes, now I can share it.
Okay, the floor is yours. Maybe you can present yourself. As I think many of our participants know you already, but maybe you want to present yourself and then, yeah.
Okay, I will. Okay, right. My name is Professor Carmel Caruana. I'm head of medical physics at the University of Malta. And today I would like to tell you something about the profession of medical physics. What is a medical physicist? Now, I'm sure many of you will have heard a bit about what we do, in the sense that either we take care of medical images, for example, or we involve ourselves in radiotherapy and cancer treatment, or perhaps even what we do in nuclear medicine, okay? And these are all true, and we'll be speaking about those a bit. But I would like to focus on the essential thing of why there are medical physicists in hospitals. Why is it that society pays us quite a good pay for us to be in hospitals? Why is it that the European Union has put out a directive, and in this directive it says that there must be medical physicists in hospitals? Why is this? Look at this. Hospitals are full of very sophisticated physics-based equipment. Yet the people working in hospitals know very little physics. Now, this is a major contradiction. In hospital, we have super sophisticated equipment. Why is it sophisticated? Because we have to take measurements on humans, on people. So the equipment, the instruments must be very accurate and very precise, because if they are not accurate and precise, that person might have something wrong with him and we will not see it. Or if it's a therapy equipment, we need to kill cancer, for example, and if that equipment is not set up properly or is not used properly, then we will not kill that cancer and the patient will die. So this is why the equipment in hospital is very sophisticated and very expensive. A CT scanner we'll see in a moment costs between 1 and 2 million euros. This major contradiction has an impact. It has an impact on the effective and safe use of the equipment in hospital. Unfortunately, we still have many people still, unfortunately, dying in hospital because we don't use the equipment as effectively and safely as we should. And it's not a few hundreds. For example, this is from an official report. In the USA, for example, United States, the number of people who die in hospitals because either equipment is not used well or the calculations for use of pharmaceuticals are not done well, or things like this, are about 100,000 per year. Not 1,000 or 10,000, 100,000 per year. These are people who have died in hospital every year. In USA hospital, not somewhere in some third world, very poor country, because of the mistakes that are done in hospitals. So hospitals are full of high-tech equipment and software, which is all physics and mathematics based. Medical equipment is a major investment of the healthcare system. A CT scanner costs over $1 million. Today, the modern ones, close to 2 million euros. Yet medical doctors and other healthcare professionals have insufficient knowledge of physics to use the equipment to its full capability and in a safe manner. And the situation is getting worse. The reason is that the technology is expanding so much faster. Here, whilst I'm talking to you at the moment here, I'm sure that Siemens and Philips and GE and Toshiba, they are going to put out new equipment the next month, new software, update of software. Yet the education of the healthcare professions is not keeping up. In fact, sometimes it's becoming a bit worse because they don't know any physics or very little physics. this is not a problem of one country or the other. It's a problem across the world. And this is why medical physicists are required by EU law. Over here, I said that the medical equipment is a major investment of the healthcare system. Our health is our most precious possession. So every country in the world spends a lot of money on healthcare. In fact, healthcare is the third biggest investment of money in the world. Healthcare is the third biggest investment. The second is energy, of which obviously nuclear power is part of it. And the first one, unfortunately, is still, believe it or not, the armaments industry. Okay, with the amount of money you for one just jet fighter, you will build a 1,000-bed hospital. Okay, with just money to buy one jet fighter. Something to think about, huh? So, what is the role of medical physicists? The role of medical physicists, we are a bridge. Medical physicists are a bridge between the medical equipment industry and research about equipment. And these are producing equipment all the time, and research is being produced all the time. And hospital management and healthcare professionals and specialists and patients who don't know any physics, so do not understand the equipment. Many of these cannot even read the user manual. This is not their fault because they are ignorant or something like that, because they have to learn many other things. They have to learn a lot of anatomy and physiology and a lot of it. So there is no time to learn also the physics. There's simply no time. So, but this is a problem that the world has to face. There is this major contradiction. And we as medical physicists try to bridge this problem. Okay, I always say medical physicists have one foot with the equipment and the industry and one foot with the healthcare professionals. Now let's look at some specialties of medical physics in the nuclear and radiation field. And we'll look at the three most important ones. They are diagnostic and interventional radiology. Many people call it also known as medical imaging, nuclear medicine, and radiation oncology. Many people call it radiotherapy. And I'll give you an indication of what is the role, many roles of medical physicists in each of these, but one very important role. Let's look at what diagnostic and interventional radiology is. Okay, these are medical images. We want to see images of the inside structures of the inside of the body without opening it up. Why is this important? Because, for example, suppose somebody has problems with his heart, okay, with the valves in his heart. Now, theoretically, you can put the patient down, put the patient on a surgery table. You can give him full anesthesia. Then you can start cutting here, okay, all right. You can saw through the ribs, move the ribs sideways. Okay, you can move the lungs a bit, you can reach the heart, you can open the heart and check what is wrong with the valves of the heart. The problem is that by the time you do that, the patient would be probably dead. Because if he has heart trouble and you put him through that intervention, okay, you kill the patient. Moreover, once you cut into the skin and inside, there's a very big probability of infection. Okay, and infection, biological infection, bacteria, is a killer of people and of patients. So we want to see inside the body without opening up. We also do it in industry. This, I mean, the people from nuclear energy will know about it. You want to see some inside without opening up. Okay, and you use X-rays and use CT scanners again. It's called non-destructive testing in industry, and in medical physics, medical imaging is non-destructive testing of the human body. And I'm sure you have seen radiography images like this. Look, these are 2D images. You have an X-ray tube here. You have the patient here. You have the X-ray sensors down here. Okay. Right, and you get a digital imaging these days, image these days, and you can see the structures. Can you see the structures? Can you see the ribs here, for example? Okay, you can see the heart. This is the outline of the heart here. Notice they're quite good images. I mean, if you have a major fracture, you can see it. Or if you have, for example, here they have put metal because the person has broken her hip here. So they have fixed it with metal. You can see it. But the images are not very good. Can you see? They are not really so good. These 2D images are not so good. When you want to make a very accurate diagnosis, that is what is wrong with the patient, to know what is wrong, they're not enough. You need to move to something else, 3D images. And in 3D images, we use CT scanners, what are known as CT scanners. And look at the images now. Notice the ribs, the images of the ribs here. Notice the images of the ribs here. What a difference. If you have a small fracture here, you can easily see it. You can see the heart. Can you see the heart there? Okay, much clearer than what you can see over here, which is just a blur. Okay. In a CT scanner, you have an X-ray tube which rotates around the patient like that, so that you can see the patient from all angles. And that's why you can produce a 3D image, because you can see the patient from all angles. Over here, you only see the patient from one angle only, from here, and you see him like that. The tube here does not rotate around the patient. Here, it does. And this is a CT scanner which has been opened up, and you can see it rotating, and don't think it rotates slowly like that. It rotates really fast, okay? And this is the X-ray tube here. These are the sensors here, and it rotates over here in the XY plane. Can you see it rotates in the XY plane, whilst the patient moves here in the Z plane, okay? The patient will move here in the Z plane. Now, we're using X-rays here, but the problem with X-rays, they are also slightly carcinogenic. That is, they bring as a side effect, X-rays can produce cancer. And this is what one of the most important tasks of the medical physicist is, what is known as optimization. Optimization, to try to produce images, clear images, sharp images, so that an accurate diagnosis can be made, but with as low radiation dose as possible. As low radiation dose as possible. Not too low either, because if you put it too low, that the images will not be good, and you will not be able to make an accurate diagnosis. Look at this, for example. With an X-ray, you can see the structure, okay, of the arteries and the veins. This is the brain. Look. Can you see? It's amazing what you can do with physics these days in medicine. Can you see up here, these two blobs here? Those are the kidneys. Okay, I'm mentioning them because I'll be mentioning them again later on, because the kidneys are used to filter the blood. So that's why they can be seen here. Notice you can see the structure of the kidneys, okay? So it's okay. Even with X-ray images, you can see the structure of the kidneys. We also use other which don't use ionizing radiation, like magnetic resonance imaging, which I'm sure you have heard. It's also 3D. Look at those images of the brain. And magnetic resonance imaging, we do something very unusual. We put the patient in a very strong magnetic field, 3 Tesla. Okay, and 3 Tesla is a very strong field, about 60,000 times the Earth's field. Not 6,000, 60,000 times the Earth field. And we put the patient in this strong magnetic field to actually magnetize the patient. We magnetize the patient because the hydrogen nuclei in the hydrogen atoms of water, and most of our body is water, it has a small magnetic moment, the hydrogen nucleus. The proton has a small magnetic nucleus. And we can magnetize the body and produce this type of images from that magnetization. Look at that. Look how strong the magnet is. That this is a real thing that happened. The guy came in with a fire extinguisher. It took the fire extinguisher complete with the man and took him inside like that. Look at this. This is a patient table, just to get like that. And you can see these incidents. If you want to go to Google and just type in MRI incidents, and you'll see a lot of them. Unfortunately, some people have died also because there were no medical physicists. Ultrasound, Look at that, what we can do today. 3D images, can you see the baby here? Can you see, we can 3D print them today also. So notice, we have very powerful imaging techniques, guys. Then another specialty of medical physics is nuclear medicine. In nuclear medicine, we don't look at the structure of the kidneys, for example, or of the organs, but we check whether they are functioning properly. What do we mean by this? For example, let's take the kidneys, okay? You have two kidneys, they are at the back here, okay? And they are like big peas, like that, like beans. They are two big beans. And you can look at them with X-rays or CT or MRI, and they might look the structure. They look perfectly normal. Okay, they might look perfectly normal, but they are not doing their functioning. They are not cleaning the blood. Okay, so their structure is okay, but their functioning, they're not functioning. Okay, and this you can only check by injecting small amounts of radioactive materials into the patient. Very small amounts, and you can actually check whether the kidneys are working properly or not. Sometimes we inject radioactive materials not to see the functioning of organs, but to kill some type of cancers. Okay, we inject radioactive materials linked to some other things. They are called pharmaceuticals, radiopharmaceuticals. And these radiopharmaceuticals with alpha or beta on them, they move to where the cancer is, and then they disintegrate there, and the emitted beta or alpha actually kills the cancer cells. This is done in nuclear medicine. And in nuclear medicine, we use what is known as a gamma camera. It's called the gamma camera because we use gamma rays. Okay, the radioactive materials give off gamma rays, and this is the gamma rays that we detect with our sensors, and produces this type of images here. Look. Okay. Notice today we even have what are known as PET scanners. PET is short for positron emission tomography, where we use positron emitter. Positrons, as you know, are electrons with a positive charge, but okay, and they produce fantastic things. For example, suppose I want to know which part of my brain functions when I hear a noise. Somebody makes a noise, for example, they want to know which part of my brain is triggered when I hear that noise. You can do that with PET. With PET, you will know exactly which part of the brain is triggered. Or when I'm talking, for example, which part of my brain is being used. I need to know that. Sometimes, for example, they need to make an operation on the brain. They need to know which parts of the brain the person uses to speak. Because if they make a mistake and cut through those parts, then the person will not be able to speak anymore. Okay, and this PET CT, so it's a combination of this positron emission tomography and even CTs. You can see, right, and even MRI, PET MRI. They are very good, extremely fantastic images. Here is one of our young medical physicists. This is a PET CT scanner, and she's doing some tests on it. Then we have radiation oncology, the final specialty. Some people call it also known as radiotherapy. In radiotherapy, we use electron or beams or X-ray beams or even now proton beams or even sealed radioactive sources to kill cancer. Okay, so with medical images, we try to detect cancer. Even okay, whilst in radiation oncology, once we detect it with the imaging, then we want to kill it. Then we kill it with radiation beams. Again, here in physics, what is the work of the medical physicist? Suppose this is a patient here and he has a cancer here. The cancer is here, but the cancer is surrounded by other parts of the body which are healthy. So how can you send the beam from the outside of the patient so that it hits the cancer and gives it a big wallop of X-rays and kill it without damaging the surrounding healthy tissues? This is a very important role of medical physicists called radiotherapy planning. And again, here it is optimization, and the optimization in this case is killing the cancer without killing the surrounding healthy tissue, without damaging the surrounding healthy tissue. Again, this is, she's a medical physicist now, an ex-student of our masters. This is our accelerator, one of our accelerators. This is a proton accelerator. It produces a proton beam. With protons, it's much easier to actually kill the cancer without damaging the surroundings. That's why we're moving a lot towards protons now. The problem is it's still very expensive. It's only found in a few countries in the world. And even in those countries where it is found, you only find very few of them. But this is the future. Then we have brachytherapy. Brachytherapy, we take small radioactive sources like this, sealed radioactive sources, and put them inside the cancer. So we can do it by surgery, for example, a small incision, and they are put inside the cancer to kill it directly. Sometimes it's done through other means. And here you have a medical physicist. Look at this is the type of equipment used, where these small pellets, sort of, they go into where the cancer is and kill it directly. Hospitals are full of sophisticated software. Look at this type of software. Look, 3D imaging here. Can you see? This is the CT image, and this is how you render it in 3D. Look at the kidneys. Can you see? These are the kidneys here. I told you that they are bean-shaped, the kidneys. Okay. Can you see here the hip bones? Look, this is the backbone here. Okay. Again, radiotherapy treatment planning software. This is the software which is used, fantastic software. It's based on something called Monte Carlo mathematics, Monte Carlo techniques. And the software helps the physicist how to hit the cancer without hitting the surrounding healthy tissues. Fantastic piece of software, unbelievable. So what will you do in medical physics? Why is important to have medical physicists? In medical physics, you learn both physics itself and its medical applications. You use your physics knowledge for solving real-world challenges and improving the health and well-being of people. So it has both scientific and social value. This is one of the things why I like medical physics. Yes, there's a lot of very good science, very good physics and mathematics in it, yet it has a social value. You help people directly by saving their lives. You learn about some of the most sophisticated equipment and software used in clinical medicine. You involve yourself in interesting and challenging work. It's never boring because healthcare technology is continuously changing. All the time. Even I, as a professor of medical physics and only in medical imaging, I can't keep up. I can't keep up. They're putting out new equipment all the time, all the time. This has the advantage that you are never bored because the things are always moving. But you also have to realize that you can't try to learn everything. It's not possible to learn everything anymore. Learn how healthcare technology is used to take care of your health and that of your family and friends. One of the nice things about medical physics is that you also learn about what happens in a hospital and how you can take care of your own self. For example, some time ago, I had a small operation, and as a medical physicist, I read about it first, okay, and I realized that they forgot to tell me to do something. They forgot to tell me to do something. If I hadn't known medical physics, enough medical physics to read about it, I realized and I told them, and I did it before I actually told them. So this is one of the advantages of medical physics. You learn how to take care of your own health. I will tell you a bit now about the bachelor's in medical physics that we have in Malta. In fact, it's a bachelor's in physics, medical physics, and radiation protection. And the people who do this can go on in either physics, all areas or physics, or all the specialties of medical physics, or even the specialties of radiation protection, and not just in medicine. Now in the fourth year, they'll also be doing also a bit about the nuclear also, and about the use of radiation in industry and even in the environment, because I want them to see all aspects of the use of nuclear and radiation, because the world is changing. And the opportunities that exist today might not exist tomorrow, and what doesn't exist today will exist tomorrow. So it's important to open up their vistas as much as possible. In our BSc, we have 5 strands. We have a strand in physics, mathematics, statistics, and ICT. Then we have anatomy, physiology, and pathology. Okay, because we said that medical physicists, we have to bridge these two. We have to bridge these two. And then we have a lot of medical physics and radiation protection, particularly in the final year. The final year, there'll be a lot. Then we have hospital placements. They actually have experience of hospitals. Okay, and then over 3 years, the 4 years, they have 336 hours of this. Then obviously there's a research strand that we also involve ourselves in. After the 4-year masters, after the 4-year bachelors, and they do a 1-year masters. If they choose medical physics, they go for medical physics. Now, one of the problems that we had when we did this was that the students of this BSc, they actually go for their physics and maths lectures with the physics students, because they need to become good physicists. You can't become a good medical physicist unless first you are a good physicist. But they also attend lectures of anatomy, physiology, and pathology with radiographers, physiotherapists, etc., the healthcare professions. So that first of all, they learn about healthcare, because they need to be a bridge between here and here. And you cannot be a bridge if you only know this. You need to know both. And they get to know the other professions. This is very important, because so that later on in life they can liaise. First of all, they make friends along the way. This is very important, that they make friends while they're still in their undergraduate years, so that even some problems which exist with the adult generation perhaps they will not have it, because they would have forged friendships when they are at a younger age. But the problem is that when they join them here, in their pre-university in gymnasium, they would have only done physics and mathematics. They wouldn't have done biology. So students were afraid that they wouldn't manage to do this. So we solved this by doing a summer school for them. So before they start the course in summer, they do a pre-course summer school. It's online. Anatomy and physiology, it's not something school that they have to learn 5 days a week. I mean, they have about 3 hours per week. And it's done online, so they can do it wherever they are. So even if they are going on holiday, I mean, last year, one of the lectures I did when I was in Berlin, for example, myself, I did it to them. And others would have traveled, they can take their computer with them, and even wherever they are, even if they're on holiday, they can attend it. And it's done in a very calm manner, and it has become a very, very popular school indeed. If you want more information about medical physics, you have here the website of the European Federation of Medical Physics, of organizations for medical physics, the International Organization for Medical Physics, the American Association of Physicists in Medicine. The IAEA has a lot of information, and all free, guys, all free, entire books free. Institute of Physics and Engineering, it is of the UK, also has a lot of information on their websites. As I said, the IAEA have a lot of books. All these books are free. You can download them as PDF. Okay. In fact, my students, if they want to practically, they can not buy any books at all, but I encourage them to buy some books, because although there are many books of the IAEA, some of them are too specialized, so they cannot read them immediately. But very few books, most of them are free. And then their masters, they will only use these. And just in case you thought that medical physics is only for people, okay, believe it or not, there are medical physicists and even radiographers in the world that make more money imaging animals, things like race horses and pets, okay, than the people. They make more money, you know, these race horses, 300,000 to buy a race horse, unbelievable. So you can imagine they take x-rays of them and check their hearts, to check whether the heart of the horse is working properly. Because if the horse you buy it for 200,000 and the horse has a heart attack, he's worthless. And thank you for your attention.
Well, thank you
Kirsten,
very
I've
much.
tried to be on time.
You're perfectly on time. It's 45. There's so much going on in the chat. Maybe you want to have a look. I mean, if I try to pick one, there I would miss out of all the other interesting discussions. Maybe you want to go through the chat really from the beginning, from really when you started. There were questions coming in, and I don't know if you don't mind, just answer them.
Oh,
and,
don't worry, I will
yeah?
answer them. And here's my email, guys. If any of you have any questions, just write to me. Please put ENEN in the email header so that I will know where the question is coming from, and it's open to everybody. Please ask as many questions as you like. That's why ENEN is here.
Okay, thank you very much. So super. So the last subject of today is on radiation protection, and we have Philip from SCK jumping in for Lisanne. Are you here?
Yes, I'm here. Do you hear me?
Yes.
And do you see the presentation?
Yes, we see the presentation. Yes.
Try to put it in slideshow.
It says Tom Claris, but it's not you.
Yes.
Your name
No,
is Philip, no?
Yeah. I'm jumping in for Tom, who was supposed to jump in for Lisanne. I don't know how they arrange it, but yeah. No, the presentation was made by Tom, so I didn't change his name. So, okay, so I understand I have half an hour, yes?
Yes. Okay, please.
Okay, so I will start.
Yeah?
Just
okay,
as an
go ahead.
Thank you. So just as an introduction, so my name is Philippe van Haveren. I'm head of the dosimetry and calibration group at SCK, the Belgian Nuclear Research Center. I'm also a professor at Leuven University. And okay, so my specialty is more dosimetry, but I will talk more general about radiation protection today. Let's see. So I have a few points here to discuss. First of all, it's going to be a quite general talk and not very scientific. So I'm talking about the international and national framework, about the general principles of radiation protection, what kind of professionals in radiation protection there are, and then you have the protection of the public and protection of the professional exposed persons.
Philippe, excuse me, would you just start in slide in presentation mode?
For me, it's in presentation mode. I don't know.
No, it's for us not.
Let me start
you just
again.
click on the.
Yeah, that's what I'm doing, and I see it in.
Now it's. No, it's presenter mode now for you.
Mm-hmm. In my screen, it's just presentation mode, so I don't know what is.
Well, I think we can live with this. It's. I mean, it would show notes if you have notes, but we at least can see the presentation. We see the next slide already, but.
You see it. Yeah, I'm working on two screens, so that's probably the reason why. Like this.
Yes, like this.
Okay. Yep. Okay. Okay. Thanks. So yeah, let me minimize this. Okay. So radiological protection against ionizing radiation. So what is it? Well, we want to limit the health risk involved in the use of ionizing radiation. And we do this on a system, a dose limitation system based on an international consensus. And that's mainly managed by the ICRP, the International Commission on Radiological Protection. And this is on the basis, of course, on the knowledge, on the limited knowledge there is on the risk gained from research and epidemiological studies, but also on social acceptability of the risk. So it's not just about numbers and risk, but it's also on how much risk is the society willing to accept from the benefits of ionizing radiation. Now, international context, there are a few there are many organizations that work on radiation protection. I just list here a few which are very important. So first of all, there is UNSCARE. So this is a United Nations organization, and they make reports on sources, health, and hereditary effects of ionizing radiation. So they collect actually scientific evidence, scientific data, and they put it in reports. So on the risk, on the health effects, on what kind of sources, what kind of exposures people have. So they all collect them and put them in reports every 5 years. Then there is the ICRP, so the International Commission on Radiological Protection, and they make recommendations. So they look at these reports, they look at all the scientific publications, and they make recommendations based on that. So they are not obligatory, so they are just recommendations. But these recommendations are normally always taken over by other institutes like the International Atomic Energy Agency, the IAEA, and they make basic safety standards and other recommendations, of course, but these basic safety standards are actually the basis for the legislation in many countries. For instance, in Europe, the European Commission takes over these basic safety standards and put them in European directives. And like this, they come into national legislations. So this is a bit the different steps. So you have the facts, observation reports, among others, they are collected by UNSCARE. They are made into conclusions, recommendations by the ICRP, and they are put into directive and national law and implementations on, well, international level and this EC level, which is in Europe, an extra step, because in some countries outside Europe, they take immediately they go directly to the directives of the IAEA. But in EC, they have also this basic safety standards on a European level, which are basically the same as the IAEA basic safety standards. And these recommendations go back a long way. I mean, I will not make this into a history course, but basically there's a history of recommendations by ICRP, which has started from the beginning of the 20th century. So in the beginning, they wanted to avoid acute effects because that was the first thing that was visible from the first Röntgen radiation. And so they had a maximum allowed dose of 1 sievert per year, which would stop any acute effects. Some decades later, in 1951, the recommendation was to optimize principle. So there was clear that it was not just acute effects, but you also had like these stochastic effects, and which were unable to determine. You don't have a threshold for cancer. So the stochastic effect, like cancer, you don't have a threshold. It's not like below this value you don't get the cancer, and above this threshold you will get the cancer. No, there's the higher the dose, the higher the probability of a cancer. So this brings automatically this optimization principle. So at that time they went to 3 millisievert per week, so 150 millisievert per year. So they went further, more types of effects, like avoiding of the irradiation of the gonads. So they went to 50 millisievert and go also lower for population. So 5 millisievert per year. In 1977, they introduced the 3 protection principles: justification, optimization, and limitation. So I will go back to this as well. And they introduced this effective dose, so which is like a measure for the practical radiation protection risk. So I will also go a little bit deeper into that later. So continuously during the years, the limits have been going down. So now you probably know, or if you don't know, now the limits are at 20 millisieverts per year for workers and 1 millisievert for public. So that is, I will also come back to that as well. So there is a learning process, of course, by all these new facts. Now, the IAEA is something like UNSCARE, which is an institute of the United Nations. It's located in Vienna, and it was founded in 1956 to promote nuclear energy. So it was very focused on nuclear energy and avoid the spread of fissile materials for military use. So this is something, this non-proliferation, this is something you probably hear in the news from time to time. So that's also the IAEA inspectors that go to different countries to avoid this spread for military use. But it's also a very active organization scientifically. They publish a lot of reports. There's, I mean, if you're, you can go to this website and get alerts, and it's almost like every week there's new reports coming out from agency, or even every day almost. They organize tons of conferences on teams. And you have also this RPOP website. If you go there, it's a lot of medical things, but just go to this website and you will have continuous update of new information about radiation protection. So it's not just nuclear energy, it's not just non-proliferation. There's also a big part of radiation protection done at the IAEA. And one of these things is these directives that they publish every, let's say, 5, 6 to 10 years. There's a new basic safety standard. So it says what the name says it already. It's an international basic safety standard. So it gives the basis for all protection against and the safety of radiation sources. So this is the last one published. And as I said, in Europe, the Euratom, a part of the European Commission, they adopt the ICRP recommendations and the IEA basic safety standards into the European directives. So the directives from the agency, the basic safety standards, are translated into a European context, and they're basically more or less the same. So we have the radiation protection units, equivalent effective dose. I will tell a little bit more about this later. In this whole basic safety standards, there are different kind of activities. You have the planned activities, existing activities, and exposure in emergencies. So these are different kind of activities which require different type of radiation protection. I said already, there's the three basic principles: justification, optimization, and dose limitations. And then you have the concepts of dose constraints and partial exposure, which are also introduced in this latest Euratom directive, which was from 2013. So these directives are actually the fundamentals of radiation protection of workers. So you have the directive for workers, and you have one for patients. I will talk about the patients later. So for workers, so these are some basic steps there, which would make sure that the workers, people working with the ionizing radiation, are protected. So first of all, you have to do some risk analysis. So the type and amount of risk has to be evaluated in advance. The workplace has to be identified in controlled and restricted areas. So this, if you go into some area, some institute where they have ionizing radiation, you should in principle everywhere in Europe have the same rules for going to. You have controlled area and restricted areas, and the same rules apply there as well. The exposed workers, they are also classified according to Class A and Class B of exposed personnel. So that's also something which should be harmonized over the whole of Europe. And when are you Class A? Well, if you have the risk of having more than 3/10 of the dose limit, the dose limit being 20 millisievert per year. So if you have a risk of having more than 3/10 of this dose limit, you are a Class A worker, meaning that you will have to wear, for instance, a dose meter. There's other rules for that, but that's one thing. If you are Class A, you are obliged to have a dose meter to measure your radiation. A fourth basic point there is the implementation of supervision measures. So if needed, this individual monitoring. Could be area monitoring in zones where there's less radiation, could be enough, but if you have higher radiation, you have individual monitoring. You will need medical follow-up of the professional exposed personnel. And you will need to inform them and train the workers and the students for the health risk. So they have to be informed of the health risk. Special attention has to be given to pregnancy and breastfeeding. You have also the medical exposure. So that applies to patients and also to persons assisting patients on a voluntary basis. So there the principles are a bit different. So you have the health monitoring of workers, the population screening, biomedical research, medical juridical exposure. So these are also topics which are handled in this medical exposures. This does not apply to the persons performing the medical exposure because those are the workers. That's the other part, and also not a member of the public. The public is also separate. So, and basically, if you talk about patients, then only two of the three general principles apply. So you have justification and optimization. You have no dose limits. You have dose constraints instead of dose limits, which is of course quite logic. I mean, if you go in radiotherapy, you need to have a high dose to kill the cancer. You cannot say we have a limit here and then we stop treating the cancer. No, also for having the chest X-ray image or something, there's no limit to the dose you get there. No, the dose should be such that the image is appropriate for the goals. So you have optimization, of course, and this is this reference levels, for instance, diagnostic reference levels. You know that if a normal for a certain chest X-ray, for instance, there is a diagnostic reference level where in principle you should be below. If you are above, that's possible, so it's not a dose limit, but if you are above, there should be good reasons for it. So it's a bit different than for workers where optimization is always, it's different. Justification is of course also possible. And who will do that? Well, there's on different levels. So you have level one is if there's a new medical technology, then it has to be at a certain level for this is the healthcare sector that has to check this. On level 2, there's medical technology for a certain application. For instance, can we use CT for lung cancer screening? I mean, do we detect more lung cancers than we induce them by giving the dose? And then level 3, application for a certain patient. So on a specific personalized method. So that's the doctor actually. So you have different levels of justification, whether it's a whole new technique for the whole world, let's say, you have for a certain application and for a certain patient. So this is justification. And then, as I said, there's dose constraints instead of limits. So you should have the dose as low as possible, but there are no limits. Now, this optimization, as I said, it's always a trade-off between dose and image quality. In the previous talk, you could see very nice images. In principle, the more dose, the more irradiation you give, the nicer your image will be. So you can make perfect images of whatever part of the body if you give enough dose. Of course, that's not good, because the more dose you give, the more health effects you will induce as well. So there should be an optimum, a trade-off between the best dose you give and the best image quality, the lowest dose and the best image quality. So it could be for having a fracture in a bone, it's possible that you give a much worse image as long as you see the fracture in the bone sufficiently. That's enough. So in radiology, this X-ray exposure versus the detail of soft and hard tissue is a quite important balance. The same with nuclear medicine. You inject a certain amount of radioactivity and you measure a time to acquire for a certain diagnostic image. So that's why, as I said, there are these diagnostic reference levels, so which give you an indication whether normally if you're below, then it's good practice. If you're above, you have to check whether it's not bad practice. There are regular audits for different hospitals and countries. I mean, in principle, that should be organized. And then you can, for instance, see that if in one hospital they give constantly double the activity than in another hospital, then there is something wrong. You know, that's how you can determine these reference levels. The same for therapy. There's also a trade-off between therapeutic effect and detriment of the healthy tissues. You can give, of course, hundreds of gray, and then you are sure that the tumor cells are dead, but then you kill, of course, also a lot of healthy tissue, which is not good. So also there has to be a trade-off between the best dose and the lowest dose and the best effect. The same for nuclear medicine. For nuclear medicine therapy, you have to have the best activity that is possible. And all this, there's an important role to play by the medical physics expert, the MPE. So the quality assurance, patient-specific dosimetry, optimization of the clinical practice, these are all tasks of a medical physics expert. Well, this is a bit repetition. So you have the basic scientific studies. They are collected by UNSCARE. BEER is another organization that's more on, they collect more data from the atomic bomb still from in the World War II. You have the recommendations. You see there are other regional standards, regional institutes that collect these data and they give recommendations, but the basic ones come from the IEA and they go to the national regulations. You have also professional organizations like IRPA, which is the International Radiation Protection Association. So all the radiation protection experts are in principle collected there. You have standard organizations, ISO, IEC. You also have ICRU. So this is the International Commission on Radiation Units. So all the sometimes complicated units are also in another institute. So as I said, there are many of them. Now let's go a bit deeper into this general principles of radiation protection. So as I said, justification, optimization, dose limitation, and they have to be balanced against each other. The advantages of the application compared to the disadvantages, which will be health risks. And this gives you a net benefit. Now, this justification means that actually every use of ionizing radiation has to provide the society more benefit than the damage it's causing. And the benefit does not necessarily has to come to the persons exposed. And the same, the health is not necessarily, the health damage is not necessarily to the persons that use it, the ionizing radiation. So there's no need to choose the option that goes with the lowest exposure, but the advantages have to outweigh the disadvantages. And there you have to consider everything, politically, economically, and social aspects. As I said before, this is in medical justification is also you have to have sufficient benefit when the whole potential of diagnostic and therapeutical advantages outweigh the risks. Second one is the first you have to justify, and once it's justified, you have to optimize it. And optimize is most commonly described as ALARA. You will hear this term ALARA many times as soon as you start working in this field. There's a lot of applications of ALARA, and ALARA means as low as reasonably achievable. So that's very general, but that's quite a good concept that's been devised some years ago. And of course, the question is, what is reasonable? What is reasonably achievable? So optimization is like an iterative process. You need continuous revision and evaluation. And you have to try to prevent and reducing the future exposure to ionizing radiation. It's something you do in advance also. You have to plan in advance your intervention. You have to plan what you're going to do. And like this, you can optimize it. There's no use just looking at it once it's already done. So for instance, you have dose reference levels, the DRLs. That's an example. You think, okay, we're going to do this kind of work. In other situations, this was the dose that was achieved there. So that's something which is achievable. And this is reasonably achievable because in other countries and other examples, they have done this. Also here, you have to take into account technical and economical factors. I mean, you can probably reduce the dose with a factor of 100 if you invest €1 million in a robot that does it for you. But that's, of course, not always the best economic factors. So you have to take all these things in account. So optimization mostly is taking 3 parameters. So you have the time, distance, and shielding. So these are important principles of radiation protection as well, of course, but I assume you know this. You have to reduce the time, increase the distance, and use shielding if possible. The third principle is a dose limitation. So the sum of the received and the expected dose may not exceed the limits. So again, this is not for medical exposure, this is for workers. What are these dose limitations? Well, for the public, this is 1 millisievert a year. For inhomogeneous radiation, you have, for instance, for the skin of extremities, it's a maximum of 50 millisievert per year, and for the islands, it's 50 for the skin and 15 for the islands. So these are the dose limits for the public. Now, you know, these dose limits are lower for public than for workers. And why is that? Well, of course, because the public also includes mainly the children. So workers, you don't consider people under 18 as workers, and they are simply more sensitive to radiation. So that's why to get the same effects, the same acceptable effects, you will have to have the dose limit for the public lower than for workers. For the workers, as I said before, at the moment, this is 20 millisievert per 12 consecutive months. The millisievert, 20 millisievert, this is effective dose, which I will explain. Again, also here we have extra dose limits, because it's not because if you have an effective dose less than 20 millisievert, that does not mean that your individual organ or skin could have a very localized inhomogeneous irradiation, and it's possible that your skin has maybe 1 sievert while your whole body has only 1 millisievert. So that's why there are extra limits for the skin, 500 millisievert per 12 consecutive months, and for the islands, also 20 millisievert on 12 consecutive months. It's important that this dose limits is not dose credit. It's not like, oh, I have half-year work and I still only have 1 millisievert, so I can spend another 19 millisieverts for the next 6 months. No, you have to always think about the 2 first principles, of course, justification and optimization. You have to have this low as reasonably achievable. Just 1 minute about the quantities, as I am working in dosimetry. For me, this is all. This is a basic thing, but you might be confused sometimes if you hear sieverts and gray and kerma and fluence and dose and all these things. Well, basically, this figure gives you a bit of background on how to frame these different quantities and units. So you have the physical quantities, which actually describe the source. So you have a certain source, And what does it give? So it's independent of the person there. So it's affluence, number of particles per second, number of particles per surface. You have the kerma and you have the absorbed dose. So kerma and absorbed dose are energy deposited in a certain mass. And so this is not talking about which mass, not talking about a person. No, this tells you how strong a source is. Then you have the protection quantities. So the main important one here is this effective dose. So this gives you the link with the risk. So basically, 1 millisievert of effective dose, this gives you a certain risk of a cancer. For instance, if you have 1 sievert of effective dose, this will give an excess risk for cancer of 1 per mil. So 1 out of 1,000 excess cancers will come when you have 1 sievert. And that's why you go to this 20 millisievert, because if you assume that you work 50 years and each year you have this maximum 20 millisievert, you will have 1 sievert at the end of your career. And like this, you will have a 1 per mil chance, excess chance for a cancer. So the effective dose is basically the sum of the absorbed dose of all your organs. So it's something you cannot really measure. So it's a number which is directly related to the risk, because that's how they do it in epidemiological studies. They calculate the effective dose and see how much risk there is. So there is a straight line between effective dose and risk, but you cannot measure it because it's just the sum of doses in different organs. And that's why we have these operational quantities. And this is what the dose meters will measure. So this effective dose is in sievert, the absorbed dose is in gray, and the operational quantities is actually what you measure, and they are in direct relationship with this effective dose. So if you have your dose meter that you will wear will not measure effective dose. This will measure the personal dose equivalent. So these dose equivalent are actually the operational quantities. And the thing is that they are pretty similar. I mean, they are devised, they are defined such that the HPD is almost the same in most situations as effective dose. And this can be measured. This is a 1-point measurement. So your dose meter, if it's calibrated in HP10, for instance, then it's a good estimation for effective dose. So that's a bit background about quantities, which is not the purpose of this lecture, but okay. Okay, protection of the population and environment. I think I have about 5 minutes left. So there's a lot of protection to be done. Those were the principles that I said in the beginning, but the population and the environment have to be protected. So there's control and inspection by the regulatory authority, by independent organization and experts, and of course by the license holders. So there's management of incidents and anomalies. There's monitoring of the environment. For instance, in Belgium, you have this Telerat system, and I think you have it in most countries. There is a system of fixed monitor points in different places in the country. Each country should also have like an emergency planning system, a national emergency planning system, internal also per facility and per installations. For instance, this is the Telerat, so we have these measurement stations at different locations, and all these little dots here are one of the measurement stations. And you see that they are a bit centered there where there are some nuclear installations. So actually, I'm here in the middle of this blue at the moment. So this is monitored, and you see that this gives you also a map of the intensity of the radiation. And you see, for instance, in Belgium, if you are from Belgium, you know that the south of Belgium is like hills and more forests, and the north is more flat and closer to the sea. And you see, because we are more on hills, there's more radon, so there's a higher dose rates there that you can measure. Okay, these are more detailed about the blue points, not so important. So all this emergency planning, so we have regular exercises. For instance, at our institute, we have 2 yearly exercises of the emergency. We have these tools to calculate, suppose there is an accident, where the isotope, where the radioactivity will go through based on the meteorological information. And this is actually around all the nuclear sites in Belgium, and I guess in all countries. Now, I told it a little bit. You have some professional professionals in radiation protection. Basically, you have the RPE and the RPO. The RPE is the radiation protection expert, and that's the one giving radiation protection advice. The RPO, sorry, is the one that oversees the implementation. So that's really the one on the field, which is designated by the undertaking, by the license holder, to oversee the implementation of the radiation protection arrangements. So the health physics group of an installation, they have also different tasks there. So they have to oversee the installations, of course, the approval, the plans, applications. They have to mark discontrolled and restricted areas. They have to have an inventory of the sources, clearance, decommissioning. They have to make sure that there is means for protection and measurements, control of existing and new installations, verify the functions of all the equipment. They have to oversee the transport. They have to do they oversee the measurements and determination of the doses, and they have to be ready for incidents. This was already, I will skip that because it was mentioned by the previous speaker. So protection of workers, as I said, yeah, as soon as there is over 1 millisievert of effective dose, there is need for information and training. So this is this class B, and so for now, over 1 millisievert, you are class B. Over 6 millisievert, you are class A. But even for class B, there is the need for information and training, personal means of protection, medical follow-up, dosimetric follow-up. It's not obliged, it's recommended, and protection of the unborn child. You have, of course, I mean, this is just a half an hour, so short introduction on radiation protection, but there's a lot of means for protection. So there's this PPEs, there's the personal protection equipment for protection against external radiation and protection against contamination. If you sometimes go in a hospital, you see people walking around like this with this lead apron that protects them from the radiation. You have gloves with lead in, you have glasses, goggles with lead in to protect the eyes. You have overshoes, you have overalls, you have masks, all these things to protect against radiation. So there's a lot of things to implement for it. Of course, there's individual monitoring for the personal dose meters. And the goal of this is for verification and respecting the legal dose limits, for indication of bad practices, and estimation of the dose in case of an accident. You have different ones. I think in the past it was more film dosimeters. They have disappeared more or less. There's still quite a lot of TLD, thermoluminescent dosimeters. A lot of people using optically stimulated luminescence. So these are like passive dosimeters. And then you have something in between, which is a insta-dose or direct ion storage. This is one dosimeter where you don't have to return every month anymore to your dosimetry service. You have, of course, also the active dosimeters, but they are not for legal dosimetry. They are more for optimization purposes. You have extra dosimeters, like I said, this is the active, an example of the active. You could have ring dosimeters. You have sometimes eye-lens dosimeters as well. So then protection of occupational exposed persons, there's medical supervision. So there's a specialized occupational physician who had to follow extra courses for ionizing radiation. So this is a compliance of monitoring for classical risk and specific radiological risk. So each year or every year you go to your occupational physician, you check for the dosimetry, contamination measurements, investigation of possible accidental exposures, and there could be specific controls depending on your risk sheet. Okay, I went pretty fast because I see the time is up, so I will stop here. And yeah, that's it.
Well, thank you very much, Philippe, for jumping in, for Tom who jumped in for Lisanne, and for giving this very interesting presentation. I think it nicely also followed up from Carmel's presentation, because I see that you answered some of the questions that were asked during the presentation of Carmel. Can you remind me, there is also a natural exposure obviously to radiation. How does this line up to the 1 millisievert you were mentioning for the public?
No, the 1 millisievert for the public and the 20 millisievert for the workers is excluding natural radiation. So of course you don't count those in that numbers. I mean, if a worker that wears a dosimeter, this dosimeter will also measure the natural environmental radiation, which is there for everybody, but this is always subtracted from it. So the 20 and the 1 millisievert is really for the artificial radiation, which is made by humans. So the radon and things, radon can be, if you're like a mine worker, then the radon is an occupational source. But in general, like in a nuclear power plant or whatever, you have to subtract the natural background radiation.
And on what is a typical? I know natural background radiation varies obviously depending on where you are, but what would be well?
I think it's about 2 millisievert or something, but 2 or 3
Okay.
depends. We know that, for instance, about natural background radiation, it really depends on the location also. I know, like where we are, this is about, let's say, 1.5 to 2 microsievert per day. This is for external radiation. But there's different parts. So you have the external radiation, you have also internal radiation. So if you count all of them up, I think on average about 2 millisievert per year. But external, it's like between, let's say, 1.5 and 3 microsievert per day. And if you're in an airplane, for instance, if you sit in a plane, you can count about 10 microsievert per hour, something like this.
If you go skiing, I understand it's also a bit higher.
Yep.
Well, there's a lot of the chat is very, very active. It's Carmel also still answering questions. I see one question related to your presentation was related to this 500 millisieverts for skin exposure in 12 months. Or what did you say there?
Yeah, that's also in 12 months. Yes, 500 millisievert for the skin. So that's a limit for deterministic for a tissue effect, basically. Yeah? So if you have to make sure that the highest part of your skin, the part of the skin with the highest exposure should be below 500 millisievert. So that's the limit, which is a difficulty to do. For instance, I mean, the most people that wear ring dosimeters, one example is people working in nuclear medicine that fill the syringes and inject with the patients, and then they wear a ring dosimeter. But basically, probably the most exposed parts are the tip of the fingers, because they take the syringe like this. I mean, there's some shielding, but still, and the ring dosimeter might be here. So that's difficult to estimate because you cannot put a dosimeter on your fingertips, very difficult. So that's a difficulty. So normally you need to use correction factors, but the 500 millisievert is per year, per 12 sliding months, and this is a limit for deterministic effects. If you go above, then there is a risk for, like, you get some irritation of the skin, you can get ulceration, a small redness of the skin, which normally goes away. But if you go like to sieverts, then it can go worse and worse.
Okay, well, thank you very much. Very interesting, and I also see in the chat the positive remarks. We are obviously let's try and keep our half an hour delay. So let's say we make a short little break, just a 5-minute break. I don't know, Sila, whether you want to say something. First, I wanted to thank you, Philip, for this nice presentation. And also let me say that all presentations will be available afterwards. So we'll send them to you, and also we are streaming actually now this session on YouTube, on the ENS YouTube account, and obviously the streaming will remain available there, so you will have all the information afterwards. Okay, so let's just make a little short break, about 5 minutes.
Yes, Kristen, 5 minutes break, but after that, I'm going to say there's some useful information for the students. And after the useful information, we are going to run the first individual quiz.
Okay, good.
And 5 minutes for break.
5 minutes for break. So let's say until 5:30 break. Just a question to Mattia, our quizmaster. Mattia, are you there?
Yes, I am here.
Yes. Will you send us a link for the quiz?
Yeah, sure. I was sending it so people can start registering, and then we can start.
And Mattia,
yes?
before this, we have to tell them that everybody have to make. I don't know how to say their signature for registration for own name, because after that we cannot know who is who.
Yeah, sure.
The more important.
Yes,
that
yes.
Do not use any, I don't know, kit, flower, and anything, and X-rays, and everything. Has to use your own name, because after that nobody knows who sent the answers.
Yes, sure. Only name and family name.
Yes,
Okay.
for the whole name, because there is a lot of people who has the same names as Adriana, or I do not know, Paulina, and Paulina 1, 2, 3, 4, and nobody knows who is the Paulina. Okay.
So 5 minutes to change your name and your profile to your real name and register to the link that Mattia is sending to everybody. Okay, see you at 5:30. Bye. 5 minutes. Okay, I'm back. Matija, maybe first. Matija, can you hear me?
Yes, I'm here. I'm just trying to fix some problems, seems to be.
Okay, Matija, then
yes?
I will first to show some useful information, and now you will have a time to solve the problems.
Issue. Okay.
Good. I try to share my screen. Okay, now can you see?
Yes, we can see your screen. Perfect.
Okay, thank you. Have a nice to see you all and have meet, because I think we have a lot of emails that we changed for the last 3-4 months, and I hope that this program will be interesting for you. Instead of that, it's an online course, and always the online course is a little bit harder to organize. Now you can see the program. This is first for the medical physics part. The Monday is same, you can see, and also the Friday will be the same for the both groups. And here on Thursday afternoon, we will have a career guidance for all participants. Now, as you see that I canceled the team quiz, how I mentioned in the beginning, it will be too hard work, too much work for the online course, and I think this task, what we give you, it will be enough. The program for the medical physics will be always on Tuesday, Wednesday, and Thursday morning, and after that for the nuclear energy will be afternoon. First, we have a session for the presentations from different topics, and after that, some laboratory works. Laboratory works will be from video based, or some presenter would like to have the, how to say, live laboratory work. We will see how does it work. And you will also have 2 different quiz. One quiz individuals for the medical physics in the morning, and after that you will have a special separate quiz individuals for the nuclear energy. It means today you will have the same quiz questions, all of you, and after that for Tuesday, Wednesday, and Thursday, it is separately for the group for medical physics and the group for nuclear energy. Now, I also would like to introduce our local organizers from European Nuclear Society. Kirsten, she is today our moderator, Emilia Yanis, and Mattia Baldoni. Mattia is our quiz master. And Emilia will be responsible for the career guidance. And I would say some word about awards. The first award is infographics, the 5 best infographics related to all nuclear science, the board group together. We received some awards. Very important that the deadline for submission is 6 July midnight. It means that 6 July, tomorrow on midnight, please send me the infographics on my email address. Because the reason is why we ask for 6th July, because I would like to put in an ENEN Facebook all infographics, and for the most popular who received the highest number of the like of the videos. You can share this, but please ask everybody to make a like on the ENEN Facebook site, because other case I cannot number it. Please use this ENEN Facebook. Then the infographics can submit it individually or as a team. It's absolutely not important that you would like to make individually the infographics or as a team. How I mentioned it before, I send it in a letter, and I also put it on the Facebook group. Then for the best videos related to all nuclear sciences also, the deadline is the same for the same reason, and also please send me the link where I can find the video. You can put in some drive and I'm going to download it. And the same award. And if somebody cannot finalize, cannot finish the video or the infographics, but they would like to take part in the competition, you can do this. But in this case, cannot go for the most popular video, because all the videos and all the infographics I'm going to upload at the same time. Then the third kind of awards are team project awards. You can find the project task on the on the competition, on the summer school website. And the deadline for submission for the project works is 8 July, it's Thursday, and at 8 o'clock in the morning, because for the jury, we need some time for the evaluation of your work, of course. And there is a 6-8 pages written text in PDF, and it's recommended to make 6-8 slides for presentation on Friday, because on Friday we will have a special project presentations for the best projects. Then about the teams, the team has to consist of maximum 3 students. You can make a project for the 1 person, for 2 persons, but maximum 3 persons, because other cases it will be a lot of people in the same group. For the teams can be formed by participants themselves. This was the reason that I made these Facebook groups where you can find each other, and now I received a lot of emails about who make the groups and who will in the same group. If you form the group, please send me the names and the name of the group, that after that we know who are involved in which team project, of course. When you send me the project work, please always put the name of the teams and who are in the team, the names of the students. Then also these project works have to be sent to me in this email address. You can also use the other one, what I use for communication. It doesn't matter, but I like mostly this one because it's always work. Then criteria for scoring. Videos, infographics, projects, works have to possess scientific merit, be creative and interesting, have an attractive design, and be of high quality. I think it's very important. We will have an international jury from our lecturers, and they will score each of your works. Then we have individual quizzes, free best students from both topics. It means free from the medical physics and free from nuclear engineering. Every lecturer and laboratory work leader will give multiple choice questions, and those who give the most correct answers in the shortest time. We can see how correct answers we received and the time when you send your answers. Then mostly we have 15-20 questions daily. Depends on the presenters, the lecturers, and always more answers for each question, but only one answer is correct. Always only one answer is correct, and the answers will be evaluated every day. After that, Mattia will summarize the score on Wednesday, because it is the last day for the quiz. But the results, when we combine all the results, all the good answers and the time announced on Friday during the award ceremony. And what is very, very important, please use your own name. Other case, we do not know who is the participants, and we cannot recognize their answers. Then for career guidance organized by the ENS, the responsible is Emilia Yanis, and we will have special people who can give to you any recommendations, suggestions, who can answer on your questions. And here is some people from the European, for the SCCAST and more Belgium, then European Nuclear Society Young Generation Network. Also we have from IFOM side, from the radiotherapy and radiology and imaging. If you have a questions, you can ask them. The project presentation, the best project work can be presented on Friday in the morning. Every presentation will have 10 minutes. The program will be compiled on Tuesday afternoon after when we receive the project work and we evaluate it. Also, we will have a roundtable discussion. We are organizing it on also on Friday. We are interested about your opinion about the online summer school, about the online education, and about how the ENEN could facilitate the work of bachelor's and master's students in the future. And please let us know if there are volunteers who would like to participate on this or this discussion, who can tell a little bit longer their opinion. And of course, we are going to discuss all questions, what is fit on the time. And that's all. I finished it. If you have any questions, please let me know.
Hello, Sila. So thank you very much. I put Emilia's email address into the chat. I think you put your already on the slide, but we can also put it again in the chat. So it's silapresnak@gmail.com. This is the one which is easiest for you, most visible. I saw two questions passing by. One is again about the deadlines. So there's a very short deadline, I understand, for the projects to be delivered. So only by tomorrow evening, for those who want to participate in the most popular video.
Yes
whatever.
and no, because we sent it 2 weeks ago. Or the project task was on the website.
Okay, so this is for the, but this is only if you want to participate in the most popular video and project competition.
Yes, it is only for the most popular.
Exactly.
Other case, it's Thursday
exactly.
at 8 o'clock in the morning. And I see that Tobias, you do not necessarily to go on Facebook. All information I send to you also in email for everybody and to you also. No any special information on Facebook.
I think also for the creation of groups, so you don't have to be in Facebook
yes,
to be in the groups.
But in this case, it's a little bit harder to find the partners who can involve in your teams, but you can write me the letter and I'm going to ask others who would like to work.
Exactly. So if you don't want to,
who are not in a Facebook, yes.
Yeah. So if you don't want to,
we have this situation and it's work.
Create your group on Facebook, you just write to you and.
Yes, it is just to make it easier to find a connection.
Okay.
Not mandatory.
Good. So, okay. And I think Mattia was sweating to get the quiz up and running. Mattia?
Yeah, no, I fixed the problem, but I had to reverse just the order of some question, but everything is okay. And so also I see 40 people that subscribed. So I think we are almost all ready to start. I'm now going to share my screen also in Zoom, but I suggest you to follow in the quiz and go on your internet browser where you registered and so on. So the video quality will be absolutely better, I think, rather than on streaming like on Zoom. So just let me start sharing my screen and then we can start the quiz.
Okay. So this Zoom screen now is only for the public, and yes, you exactly. all go to your app and have a look at your app. And yeah, I think Mattia, you're ready to go. I let you run.
Yeah, people joining again. Okay, 39 people. I think we are all ready. Yes, for 43 participants. There's something entering and okay. We can. I think we can start. We have no more people. Please write now on chat if you have a problem in joining, because okay, there is already. I have internet problem. Okay. So yes, now the people are still logging in. Just wait a bit more. I can start with the question only when all people will be ready and register. So if you already registered, please wait just a bit. Okay, now we have 40 people for 44 participants, except for me, Kirsten, and Xilla. I think we are all ready, and we can start.
Okay, so you log, there's a question, how do I log in the quiz? So the answer is you register with menti.com with the link that Matthias providing, and then, yeah, you cannot see a question right now. You only will see the question.
I have to start the quiz for all people at the same time. So
okay.
I think I'm sorry for people with internet connection, but there is a continuous login, logout. I don't know how to. Okay, now we have again 40 participants. And we have to start, I think.
Yeah, go ahead. Okay.
Okay. So let's start with the countdown for the first question. You'll get point for correct answer and the time you'll spend. So the first question is, how much waste nuclear energy produced compared to the total waste from the electricity production in Europe? You have 25 seconds already started to answer this question. Okay, time is up. Almost everyone replied. And the correct answer is the last one, about 0.05%. So congratulations for the right answer. Now, the first question, I'll give you 1 minute to read it all, and then you'll have 3 minutes to make your calculation and to find the right answer. So I can read with you. Palladium 107 is the isotope of palladium with a nucleus made up of 46 protons and 61 neutrons. Palladium 107 does not exist in natural samples, but it was present during the formation of the solar system. It is produced in large quantities in nuclear reactors as a product of fission reactor with a yield of 0.14%, making it one of the most important transition metals in the fission products found in radioactive waste. So note down this data, please, because in a few seconds, I'm going to switch to the question. Just wait a bit more. I can put some background music in the meanwhile. Okay, so the question is, and you have 3 minutes to reply. The nucleus of palladium 107 decays by emitting pure B negative radiation. What is the product of this decay? So you can look the picture, and obviously I couldn't write the right form, but you can click on one of these answers. Few answers missing. Still 5 answers missing. 4 now. 3. One answer is missing yet. And the last minute countdown. And there should be only one answer missing. "30 seconds to go." And the countdown is over. The missing answer never arrived, unfortunately. And yes, most of you correctly replied. Is the second answer the correct one? So let's move to the third question. And also here, I suggest you to write down all this data. When uranium is mined, it consists in approximately 99.3% uranium-238 and 0.7% uranium-235 by mass. The nuclear fuel used in the nuclear reactor needs to have a higher concentration of the uranium-235 isotope as about 4% by mass. So you have to estimate the time of depletion of uranium resources on Earth, assuming 450 reactors running continuously with an annual requirement of around 35 tons of enriched uranium each, and without the reprocessing of the spent fuel produced. And uranium reserves on Earth are estimated at 12 million tons. 1 minute more to write down all the data here available. Okay, now we can move to the question. Again, 3 minutes to give the correct answer. Starting from now. One minute, 30 seconds left. Only 10 seconds left. And a few missing answers. The time is up, and the correct answer was the second one, approximately 133 years. So let's move to the next question. I hope you saved using the same data. The question is the same, but you have to consider that the spent fuel is totally reprocessed once. So this operation makes it possible to recover 1% of uranium-235 and 93% of uranium-238. So using the same data as before and considering the reprocessing, you have to calculate the time of depletion. One minute and a half left. And few answers missing. Okay, less than 1 minute left. Ten seconds more. And time is up. So the correct answer, yes, most of you found the right one. So approximately 166 years. Congratulations, and let's move on to the next question. So uranium-235 nucleus is fissile because it can be split into two smaller nuclei. One of the possible transformation is described into this picture. So study a bit this, focus a bit on this picture. And you'll see also later now is just a bigger size. And the question is, starting the countdown. How many neutrons are produced during this fission reaction? Now you have only a few seconds to reply, no calculation required. Hurry up. Time is up, and the correct is the first one, 3 neutrons. Now the European Union produces around 35% of its electricity from nuclear energy. But yes, I'm sorry, it was just a picture left from the first question. So there's no question related to this topic. Now we are moving, I think, to medical physics. And the next question should be about the CT, if I'm right. Yes, in the case of a CT scanner, 25 seconds now to reply to the next questions. The tube needs to be cooled using liquid helium. Patient moves along the z-axis whilst X-ray tubes rotates in the XY plane. Non-ionizing radiation is used, and the tube rotates in a YZ plane. The patient moves along the X-axis. 5 seconds left. Time is up. And yes, congratulations to the majority of you. The correct answer is the second one. Congratulations. And let's go on to the next question, number 7. I remind you now you have 25 seconds for each question. So hospitals are interesting for physicists because they are a dynamic place to work in. They are full of very sophisticated equipment and software. They employ a lot of people. They have a good salary. For good reason. But the correct one. Few seconds left. And yes, they are full of very sophisticated equipment and software, as explained Professor Caruana. Then next question, question number 8. The major advantage of proton beam radiotherapy using a cyclotron is that you need good medical physicists to ensure effective, safe treatment. It's safer for the operation of the equipment and higher dose of to the cancer while with sparing surrounding health cells, and it uses positron source to kill the cancer cells. Few seconds left. And yes, the correct is that one. An higher dose of radiation goes to the cancer with sparing surrounding health cells. Next question. 25 seconds to answer. Nuclear medicine equipment is important because it uses radioactive tracers. We can check whether human organs are functioning properly. Some of it use positrons. We need to protect patients from radiation. Time is up. And yes, we can check whether human organs are functioning properly. Congratulations. Yeah, half of the quiz. And let's see the next question. Which of the following organization represents medical physicists in Europe? So you have these 4 acronyms, and you have to choose the right one. Time is up, and yes, the correct one is the EFOMP. So congratulations again on the second half of the quiz. What kind of documents does ECRP produce? Legislative guidelines, recommendation, scientific reviews, or scientific results? As we saw in the last lecture. Few seconds left. So ECRP produce mainly recommendation. Yes, you're right. Congratulations. This is the correct answer. Let's move to the next one. 25 seconds to say what is the dose limit for patients. 1 millisievert per year, 20 millisievert per year, 500 millisievert per year, or there is no dose limit. Most of you already replied. 5 seconds left. And so for patients, there is no dose limit, as explained Professor Van Heuve before. Let's move to the next question, which is about radiation protection. What is not part of the three principles of radiation protection? Justification, optimization, dose limitation, and protection. So one of these four is not one of the principles of radiation protection. And time is up. And the correct one is the protection. Yes, most of you correctly answered. The congratulations. We are moving to the end of the quiz. Question number 14. What is the yearly dose limit for radiation workers category A? 50 millisievert, 20 millisievert, 6 millisievert, 1 millisievert. The yearly dose limit for radiation workers category A. We saw it in one of the last slides of the last presentation. Let's see. Yes, most of you correctly answered. Congratulations, is 20 millisievert per year. Let's move to the next one. What is the role of the ERP? So the radiation protection expert, so give radiation protection advice, oversee the implementation of radiation protection, check the dose limits, control the contamination. RPE, radiation protection expert. Few seconds left. Time is up. And the correct answer is just to give radiation protection advice. Now the question 16. Which of the following statements about global electricity production is true? It's based mainly on carbon neutral sources, showing a downward trend. Nuclear energy does not play a major role. It's growing year on year, except for the global economic crisis. So one of these statements is true. And time is up. And yes, the last one is the correct one. Congratulations. We are moving to the end. And we are approaching to the question 17. 25 seconds to say which primary energy source cannot provide clean electricity for electric cars? Nuclear, natural gas, solar, or wind? Very fast answer. It's not so hard, this. No calculation required. Few seconds left. Time is up. And yeah, the correct one is the natural gas. Congratulations. And then let's move to the question 18. What cannot be listed as an advantage of a nuclear power plant? Large concentrated power source, high availability, cooling of the plant has to be continuously ensured, and long operational time. So one of these is not an advantage of a nuclear power plant. So it's not an advantage. The fact that the nuclear power plant cooling has to be continuous and assured. Congratulations. Next, question 19. 25 seconds again. What cannot be listed as a disadvantage of a nuclear power plant? Load following complicated, high investment cost, safe waste disposal necessary, low operational cost. So one of these, it's not a disadvantage of nuclear power plant. Time is up. And yes, low operational costs are absolutely not a disadvantage of nuclear power plant. And then here we are. Let's move to the last question. 25 seconds again to answer. Which is the most common type of reactor in the world? Pressurized water reactor, boiling water reactor, pressurized heavy water reactor, or gas-cooled reactor? Few seconds left. And yes, the correct one is the PWR, the pressurized water reactor, are the most common type of reactor in the world. So the quiz is over. Let's see the ranking for today. The leaderboard. Oh, very close. Ivan Panchak won for only 13 points on Merelistra Recta. Third place for Ksenia Dizdar. Congratulations to all. And now we are going to calculate for the next days also to sum all the results you have, and we'll see at the end of all the quiz session who will won the prizes and the awards that Xilla showed you before. Thank you all. I can stop sharing now my screen, and Kirsten is to you.
Well, okay, so this was just quite some brain gymnastics for the finish of the day. Okay, so yeah, at the end of the quiz, it was a short day, but only half day, but a long day. I think lots of information. As Sila said, so tomorrow is a whole day, but in the morning it's more about medical, and in the afternoon it's more about nuclear energy. Each time finishing with a quiz. So yeah, so hope to see you all again with the same link. We're using only this one link that you used today to connect for the whole week. So I hope to see those who are interested in medical physics tomorrow morning at 9 o'clock. Okay, see you. Have a nice evening. See you tomorrow. Bye.
See you. Bye.
Thank you.
Goodbye.
Thank you a lot. Bye.
Bye.